Turn on recording and we will get started. Okay, so first thing that we're going to talk about, speak of, is we are going to talk about, do like a quick review of what is the cloud, what is AWS, the design guidelines of the cloud. We are going to talk about the well-architected framework. The well-architected framework is pretty much the conceptual and filtering function framework that AWS wants you to consider whenever you're designing inside of AWS. Kind of a funny little side note. This well-architected framework is almost identical to the architected framework over on the Azure side of things, because oddly enough, it was written by the same guy. And I won't get into the details around that, but apparently the gentleman went over to Microsoft and he wrote pretty much the same well-architected framework. So the cool thing about that for us as students is that when you learn the well-architected framework over on the AWS side, you also learn most of its core facets on the Microsoft side as well. We are going to talk about AWS's global infrastructure, and then we are going to do a large architectural design, talk about a design, because we're going to build the components of that design as we move through the rest of the course. So you'll see a picture of really relatively complicated design, and we're going to talk about each of those components and how they are put into place. Okay, so it's module 1, and here we are, and here's the architectural need, right? Is that it's 2000, and Amazon has a great shopping website that's really struggling to become efficient in scale. Why? Well, because their capacity, especially during November and December, is way above what it is for the rest of the year. So someone wrote a paper and said, how do we fix this, right? And they were also having a problem where things were not, they were too tightly coupled or too loosely unavailable, right? Architectures were built kind of haphazardly. And so you may know this already, but Jeff Bezos sent out an email, basically said, look, we're all using APIs. I need a well-documented public interface that can create integration and interoperability with all of our services. And then that way that can foster independence, but we also need to be thinking about how to architect properly for the long term, not the short term. We need long-term bets, right? And so not only did someone write a paper that said, hey, what can we do with our extra capacity? But earlier Bezos sent an email saying, look, we're all doing APIs or you're fired. Basically was the response. And he's like, nothing harsh about it, but this is the future. This is the bet we're going to make. So everybody get on board, right? But Amazon was still struggling to build applications, even though they had come up with the agreement to use APIs and known interfaces to integrate with each other. And it took a long time for them to provision components. And then as things were being built, there was no commonality. They didn't have a common platform for how these services on this resulting hardware were running. And so it was just scattered all over the place. So after that paper was written, I think it was 2003, 2004, about basically the initial concept for AWS. In 2006, a couple of years later, they started selling publicly SQS, which was the first service they offered, the simple queuing service, which is almost like an asynchronous kind of messaging bus, but ticketing system. And then S3 was the next service they offered, which was the simple storage service, which is not the same S3 that we know now because it's evolved so much since then. But I highlight that because cloud, in particular AWS, is basically 15 years old. Every single startup that I'm working with is all into cloud unless they have a requirement to do otherwise. And typically they're all into a single cloud. They're not concerned necessarily about vendor lock-in or going multi-cloud right off the bat. They do evolve to that, obviously, pretty quickly after the first 2 or 3 years. But every other company I've interacted with, ranging from obviously Booz Allen Hamilton and its clients to Honeywell to General Electric to a variety of companies, big, small, and whatnot. They're all either all in the cloud or they are hybridized in the cloud. And this includes Honeywell is like a 120-year-old company. Other companies like National Guardian Life and whatnot, they're all 100 plus years old, and they are figuring out either how to completely retire their data centers or they're migrating their stuff over, right? And they're trying to figure out how to shift their footprint more into the elasticity of the cloud and less into the statics of the data center. So I think Amazon posted, how was it, north of like $50 billion in revenue this year, this last year. And so year over year, they keep growing somewhere between 20 and 40%. And so, and just to say this, they are the dominant owner of market share inside of cloud. I think they have 45% of the market when I last read it. So it just continues to grow and grow and grow. So what is cloud? Because some people, especially if you've been around the block a while, like myself, if you've been in the industry for 25 years, you hear this joke of like, well, cloud is just other people's servers. But we had other people's servers prior to AWS and the other CSPs coming online. The thing that made AWS different is that everything is software-defined infrastructure. So everything's an API, every single thing, whether it's a load balancer, a firewall, a virtual machine. The only thing that isn't really an API is, for example, independent systems like operating systems that are inside of a virtual machine, or database engines that are inside of a virtual machine. Excuse me. Those are not systems that can be API managed, but everything else can be API managed, including the data you stick in any of those other vehicles other than the operating system and the SQL engine. They can all be programmatically managed, deleted, updated, lifecycles, whatever. So it's really that software-defined infrastructure makes AWS very different. Also, the ability for utility computing at scale is amazing, because you can literally test an idea, and when you're done, just give all the resources back. You don't have to worry about your hardware boundary or investment in any of those spaces. You are just like, you pay for what you use, and you let it go when you're done. In addition, with 15 minutes and a credit card, you can be global in about an hour at scale. Maybe less, actually. I'm trying to be conservative. But you can literally take your website, push it, and go global. I can spin up a WordPress site in about 10 minutes, right? And then probably another 10 minutes to upload the content, restore backups, and make sure everything's set up. And barring any domain name replication, I can actually make that site globally available probably within an hour, where anybody in the world can hit it, and at least for the static content, it's lightning fast, right? So these are the advantages that the cloud offers. Is basically software-defined everything, really dynamic abilities ranging from graph databases to firewalls or whatnot, and it's really utility computing at its finest, because you can not only self-provision, but you pay for what you need and you give it back if you don't. So it's good. Here are the 6 kind of key advantages to cloud computing that Amazon wants you to be aware of. Is that basically you can trade hardware expenditure, capital investment, and expense for operating expense. This allows you, by the way, to shift things from these massive like $100,000, $200,000, $1 million investments right off the bat to just a SIP over time as you do operating expenses. Now, don't get me wrong. It is variable expense, because if you start a new initiative or a new project, it can increase your monthly expenditure. So forecasting can be difficult, but governance and compliance policies as well as platforms can really help with that variability. Also, every time Amazon achieves a new level of efficiency at scale, they pass those savings back to us. So like they just lowered costs in the Asia Pacific region, because every time they hit a certain level of scale, they lower the cost per gigabyte, or the cost per CPU cycle, or the cost per gigabit, right? The third thing here is that you can stop guessing about capacity, which means that if you get vendor documentation that says, hey, I need a 2x16 system and I need 8 of them, and you go to deploy that and it turns out that you really only need 3, well, guess what? You can drop those 3, or you can even downsize the existing system and say, you know what? Instead of a 2x16, what we really needed was just 2x8s, right? And so you can actually 2 processor 8 gig systems. You can just drop the size of the box. And if you have everything behind a load balancer, you can actually do that without taking an interruption, assuming that your app will scale horizontally. which by the way is a best practice pattern, is to have things scale horizontally. The other thing is that because it's software-defined infrastructure, you can not only define it programmatically, which will increase your speed and agility, but this will allow you to integrate cloud into your CI/CD pipelines. You can literally spin up infrastructure as you need it to test, do performance testing, load testing, and then just drop it. And that's really going to increase your speed and agility, because if you need another box, you can just go get another box. And then this allows you to stop focusing on things like being good at running virtual machines, for example. That's not a core business for most of us. That's an indirect benefit, but that's not a core business. If you're in the business of making, what was I talking about the other day? Oh, I have a friend I was meeting. He's like, oh, well, we make wine corks. He makes these amazing wine corks, which I was like, really? And they run, servers and websites, but they let AWS handle all of that because they don't want to be good at that. That's not their core business. Their core business is designing this amazing experience around wine. And so they don't want to be good at running servers and replacing hard drives and managing websites. They will pay AWS to do that from a managed service. And I think I've mentioned already about how to go global in minutes, particularly using content delivery networks and distributed caching mechanisms, which AWS has. There's probably specific slides on this, just so you're aware, but we're gonna breeze through them. Okay. Any questions of thus far about like what is cloud, what we're talking about, the 6 advantages of cloud computing? Does anybody, or even any curiosities, anything that's just rolling around in your head that you want to give voice to? Okay. All right. Let's talk about the well-architected framework then. So the well-architected framework is a way of thinking about design practice inside of AWS. Think of this as a filtering function for the various non-functional requirements, like high availability, scalability, security, reliability. But it's also a way to like consider not just non-functional requirements, but in general how you want to arrange and kind of like present the trade-offs. Because I mean, it's always this dance between resources, right? Because like we want to like design like things to be like super resilient, 100% uptime, whatnot, but that has a cost to it. And so there's always this dance between costs, like resources, like time, people, money, and doing the most optimal thing for the business. Because I think for most of us, if we like had unlimited resources, we would design our systems to be self-healing and highly available and fully monitored. We would do all the stuff. It's not, right? Because we actually do live in a world with constraints. So the 5 pillars are really excellent because they allow you to mentally have a model for filtering your design decisions and presenting the trade-offs. Like someone might say, you know what, I want 6 nines of uptime, which by the way would be kind of ridiculous. What is that, like 8 microseconds? Regardless, let's say it's 5 or 4 nines of uptime. And you'll be like, okay, I can give you 4 nines, but it will cost you $1 million a year. And the business is like, what do I get for 3 nines? And like, well, 3 nines will cost you like, $250,000 a year. And they're like, you know what, we're going to live with 3 nines, right? And we'll come up with another plan. But that's the main thing that the well-architected framework does, is it allows you to contextualize some of these filtering functions, so you can make sure, one, that you're checking off the boxes. Do I have proper security? Do I have reliability? Is that an important thing to the business? I would argue that of all of these, obviously, security and cost are probably ones that are fairly non-negotiable. But people will suffer with less performance or even more manual work, which is what operational excellence is, or even a reduced set of reliability. But typically, companies will not compromise on security or cost optimization. It does depend on the company, because I've worked in some startups where security didn't matter. That did come back to bite a lot of them later, right? But these 5 pillars are used to help guide our decision making, right? Our design decision making. Sorry, my son lit a candle and I was just making sure that everything was cool over there. So with security, what we're focusing on is things like identity foundation, making sure that we have observability, traceability, and awareness of any issues, doing defense in depth, which is basically security at every layer. Like, how do we go from security at the edge all the way into, the first tier of our app, maybe the load balancer, maybe it's in the web server, the app server, the database server, and all the layers in between. And then how do we create awareness and how do we assess risk inside of our organization and apply mitigation strategies and even response strategies for security? And then reliability is the second tier. So we've got security and then reliability. And reliability is really about how do we stay ahead of demand? Like, how does our capacity request stay ahead of our demand challenges? How do we recover quickly from infrastructure service failures? And mean time to recovery, by the way, is one of the core metrics of the 4 major metrics inside of DevOps. What is your mean time to recover from a failure? Because in a way, that's more important than avoiding failure. And then how do you mitigate disruptions from a reliability standpoint? Like things like transient network issues, which we all know that's a real thing with the internet. But also, how do we avoid human error, and how do we test to make sure our human contributions don't cause misconfigurations and break what's happening? I think I remember seeing a statistic like 70 or 80% of outages are actually caused by human error. And how do we create tools, checks and balances that help us so that those kind of things never make it to production? That's part of the reliability pillar as well, is that automation piece, that testing piece. And then we talked about security, we talked about reliability. Now we're talking about cost optimization. Because I just mentioned that you could design the most amazing engineering infrastructure in the world, but if it breaks the bank, you're done. Your business is done, right? And then there is no more business. There's no more client. So how do you maximize and deliver the best value for the dollar for what the business is asking for? And how do you make sure there's no unneeded expenses? And then how do you optimize the limited resources you have, namely people? How do you maximize, for example, how does Heroku run a 300,000 virtual machine infrastructure? Heroku, right? The people who kind of predated AWS, who ease the delivery of applications for developers by hosting their own SaaS service, they run somewhere between 200 and 300,000 virtual machines. How does that get managed? They're not a huge company. And so when you talk a little bit more detail, they use a lot of managed services to actually achieve that, not just at the virtual machine level, but at the container level and at the serverless level. So how do we leverage services that maximize our other costs, like the human cost, not just the dollar cost? We want to lower costs while increasing the value of what we're using. So we've got security, we've got reliability, we've got cost optimization, and then this is the newest pillar, by the way. This was just added in the last few years, is that basically operational excellence. How do we create standards and consistency for how we're deploying and designing our items out in AWS to continually create this culture of never-ending improvement, improving processes, improving technologies? And how do we create visibility so that we can know ahead of time, so that the customer's not telling us when we're down? We know of problems before even they arise. And how do we deploy, update, maintain, operate, and even retire programmatically these at-scale systems that we're creating on cloud? And that's all part of operational excellence. And then last, so we've done security, reliability, cost optimization, operational excellence, and now we're talking about performance efficiency. How do we make it so that we are incredibly efficient about driving results inside of our designs and inside of our usage? In other words, how do we make very advanced concepts simple? How do we, like the other day, literally yesterday, I was talking to a friend of mine I hadn't talked to in 2 months. They run Kafka. If you're not familiar with Kafka, it was developed by LinkedIn. It's this awesome, almost like a streaming kind of data wielding platform. It's basically a streaming data analytics platform. So basically, you put data in, it streams out, and basically kicks out to a bunch of producers or people who sip off of it, right? Very much like Kinesis to a certain degree. And it can store data for whatever length of time you have storage for. But it's a really awesome product and can scale really well. I was literally talking to a friend yesterday, and he said, we're out here running our own Kafka cluster. And what we want to do is we really want to make it really simple for both our developers and ourselves. And so they moved over to like Amazon's MSK, the managed Kafka service. And they're like, because we want, and he literally used these words. He's like, because we wanted to democratize the technology as well, so that other people could spin up their own clusters without having to necessarily interfere and engage with the operations team, because the operations team doesn't need to be in that business, right? In addition, mechanical sympathy is part of this, because it's asked that mechanical sympathy is the concept that you don't use a screwdriver as a hammer, because the screwdriver is not designed to be a hammer. And mechanical sympathy is you use the service for what it's designed for. I run into this a lot with Elasticache, where it's basically an in-memory cache that you can use to cache results, but you can also do complex data structures on it. And it's funny because people are like, well, I want to use it as a database. It's like, well, you can, but it's really designed as a cache, not necessarily as like a hosted full set database. Memcache and Redis can operate as an excellent in-memory database, but that's not what the Elasticache service was designed for, right? And so you want to make sure that you're using the services for what they were designed for, because you're going to get a lot of kind of, in a sense, digital alignment, mechanical sympathy. And that's all part of performance efficiency. So those are the 5 pillars: security, security, reliability, cost optimization, performance efficiency, and operational excellence. Any questions about any of that? Yeah, can everyone still hear me? I'm hoping someone would say something if I wasn't. You couldn't hear me?
Yes, we can hear you.
Good. All right. Okay. So let's talk then about AWS's global infrastructure, which would probably be a refresher for most of you. By the way, there's new things in the global infrastructure that I'm going to talk about that are not in the slides, that I actually want you to be aware of, because there's been some new developments in the last year. I will forewarn you that some of this doesn't show up in the exam, but I'll state that when I get to it. Okay. So here's some core concepts that probably most of you already know, but it's a refresher, right? Is that Amazon runs data centers. The data centers are actually grouped into clusters called availability zones. These availability zones, by the way, are fault tolerant. They're isolated from each other. They are connected independently to the internet, and they have their own power and cooling. They are also interconnected with other availability zones through a private high-speed link. And anything that has a network card must run in an availability zone. So if it's a virtual machine and it's got a network card attached to it, that network card has to live into an availability zone. Why? Because availability zones are where subnets live, and subnets are where network cards run, right? How do we know that? Because we have our own home network. And in our own home network, we are basically running our own like private networks with network cards, wireless and otherwise. And so we are running our own subnet. Well, availability zones are data centers where things with network cards must be attached. So for example, you might say, well, Michael, what other than virtual machines would you actually have a network card attached? Well, remember, Amazon has what they call ENIs, elastic network interfaces. Those are virtual network cards. You can actually attach an elastic network card to a Lambda function. So the Lambda function runs its networking calls through that network card in a subnet inside of an availability zone. You can attach a network card to a container instance. Now, that container is running on a host, most likely, that is already in an availability zone. But remember, anything that has a network card is going to need to be inside of a subnet, inside of an availability zone, which means that it's actually in a data center or a data center cluster. Because remember, availability zones don't just have to be one data center, it can be a cluster of data centers. But AZs, or availability zones, are independent fault tolerant zones, and they make up a region. So if you have a cluster of data centers, which is your availability zone, every single cluster of an availability zone is associated with a region. These availability zones that make up a region are usually geographically co-located, means they're near each other. There's some proximity, right? So, like for example, if we're in Virginia and there's 6 availability zones, that means there's 6 meta clusters of data centers that are partitioned into 6 different partitions that make up the region of Virginia. Now, one thing that I think that's worth looking at. Let's go to the global infrastructure map. Yes. So AWS, this is actually the current infrastructure map that AWS has. Actually, I'm going to post this out. So if you hover your mouse over here, this shows Northern Virginia and Canada and Ohio. By the way, GovCloud's on here, so GovCloud East and West, because I know when you work for Booz Allen, not everything you do is public. Most of it's actually private. And so all of the data centers are listed here. Notice that Hyderabad, Melbourne, Jakarta, Spain. There's Sweden in here. I can't get my mouse in there. Switzerland, sorry, Switzerland's in there as well. And so when you hover your mouse over this, it shows the number of availability zones. So Canada, for example, Toronto has 3 availability zones, which means there are 3 data center clusters that are attached to that particular region. Canada Central. Now, how does this show up, right? Well, if we log in, assuming, I actually meant for this to be done before I got in class, my apologies. I have 2-factor. I'm actually following my own best practices. But bear with me just 1 second. I was a little behind for this one. Oh, no, not that. So how does this show up? Well, in the upper right hand side of the console, what you'll see here is you'll see all of your zones listed. And so if I go, for example, to EC2, which is the virtual machine service, and I click in here, notice that there's an instance running because I was actually messing around with Terraform earlier and actually created an instance. And if we go in here and look, there's an instance running, right? And this instance, by the way, is running in a particular availability zone. And notice this says US East 2B. If there is a letter after the last number in the code, we're talking about availability zone. If it just said US East 2, that's the region. But this has a network card, and it has to run inside of a particular data center, in this case, an availability zone, inside the region. And so when we look at this global infrastructure map, Canada Central, Ohio, GovCloud, Oregon, they all have availability zones attached to them. Now, do note that this has local zones and wavelength zones attached as well. Wavelength zones, by the way, are zones where there's like 5G stations. And this is mainly used for cellular. Obviously, that's probably pretty evident, right? Local zones are the other kind of type of physical location that you can actually run like virtual machines in. Local zones are really interesting because local zones are not affiliated with a region map. So, for example, Virginia has local zones in Boston, Miami, and Houston, right? Notice there's 3 local zones listed there when we look at the listing here. Local zones are basically remote availability zones. I don't know why they're called local zones. It's a little confusing. But if there's 6 availability zones associated with Virginia, Virginia also has 3 what we call like local zones, but they're actually remote zones. So there's actually a zone, there's a data center in Boston, a data center in Miami, and a data center in Houston that you can actually deploy virtual machines into. So there's now actually 2 major locations that you can deploy services: availability zones, which are kind of geographically near a region, and local zones, which are distributed from a region. So again, the name is so confusing, but they're local to the city. Boston, Miami, and Houston are the first cities that have a single data center from AWS in that city, but their fallback is actually Virginia. Does that make sense to everybody? So what's interesting here also is that you'll notice that I have Ohio, Northern California, Oregon, well, etc. Right? If I switch over to Northern Virginia, first of all, note that I don't have any virtual machines running here. Right? There's none running. So if I come in here and create a virtual machine, if I'm just going to launch one raw, right? And let's say I'm going to choose just your basic kind of Amazon Linux. I'm not really attached to the tier or family because I'm actually just, yeah, no, I gotcha. I'm just like interested in kind of like showing. One thing that's interesting here is that you can actually like choose subnets and create subnets that are actually in Boston and in Miami, right? So for example, I could create a new subnet if I wanted to, so I could host my virtual machine. And let's say I was going to run it in the default VPC. I can actually run this in, ooh, it's actually not coming up right now. Anyway, there used to be listings here for Miami, Boston, and whatnot. I think I have to go back and re-verify my access, but what would happen is it shows Boston, Miami, and Houston has options underneath my availability zone info. Notice that since I am in Virginia, I've got 6 availability zones. Notice it's US East 1A, B, C, D, E, and F. Those 6 availability zones make up US East 1, which is the Virginia region. Does anyone have any questions about the basics of AZs and regions? Okay. Now remember, there are local zones now that are attached to these regions, but only Virginia, by the way, and Oregon have local zones, which actually should be called remote zones because they're not local to the availability zone, to the region. So one thing to note is that communication between the regions is actually across AWS's backbone network unless you are accessing public APIs. So if you're accessing, from an EC2 virtual machine, you're accessing S3 in another region, then that actually does go across the public internet. If you are replicating data from one S3 bucket to another S3 bucket, which is all kind of private to S3, that actually goes over AWS's backbone. Here's another map, by the way, of the global infrastructure. So this is an older version of what we were just looking at. Note that Osaka actually has 3 regions now, and it's not called Osaka Local. It's just called Osaka now. There was a time when the Japanese government had asked AWS to create a backup region due to earthquake fault tolerance. And so they had created a government-only Osaka Local region, which now is actually a public region for Osaka in Japan. So we've already seen these variations, but remember, availability zones make up regions. Now, the other thing is that there are edge locations. So this is the other kind of like the third place that your data could possibly live. These are caching locations that are for DNS, CloudFront, which is the content delivery network, or if you run Lambda at edge, which means you're running some processing power at the edge close to the user. These are locations where AWS could automatically kind of cache your data if you turn caching on. Edge locations are not data centers. They are usually groups of servers that are co-located in major ISPs. Meaning if there's a major ISP in the area, Amazon will typically stick a edge server or caching server there so it can cache and redirect DNS calls, cache and redirect things like video streaming, HTML, JavaScript, CSS, images, right? These are locations where your data could be cached. Okay, any questions there? You don't usually, I don't think you can even specify edge locations. They're not like availability zones and regions. You can't tell services to run there. You can just turn them on. Okay, so here is our kind of slightly overwhelming, our large-scale architectural diagram that we're going to be spending most of the day talking about. So notice that starting from the left, you've got users who are coming in through Route 53, which is the DNS service, and they're hitting Amazon CloudFront, which is the global content delivery network. So if you're familiar with Cloudflare and Akamai or other content delivery networks, CloudFront is AWS's implementation of it, and it's really good, actually. Having used Akamai and Cloudflare, CloudFront is awesome. And then what happens is that traffic is going to traverse an internet gateway. Now, this is not a NAT process. This is not like your home router. This is an actual routable connection from the internet to these public subnets that are listed right here. So the public subnets that are listed, that I'm highlighting in red here, these are actually directly connected to the internet. And what happens is that the internet gateway is going to route traffic to an application load balancer. That application load balancer is going to then be on the public subnets, and it's going to route traffic over to these private applications. And these applications are actually going to be in an auto scaling group. So what's going to happen here is that they're going to scale as demand escalates, and they're going to scale down as the demand goes down. And then what happens is that Elasticache, which is right here with the stars, Elasticache, and they're using the memcache flavor, is going to cache any complex database queries that arise from this RDS database, which is right next to the hearts. And so one of these is going to be primary, the one that says on the primary is going to be primary, and the other one's going to be secondary. And these two memcached instances are going to cache data for these application servers. Because just to say this, one thing to note is that in this kind of scenario, the app servers are all going to talk to the primary. By putting a caching mechanism in place, this creates a local kind of source of data, so that it doesn't have to go directly down to the primary across these subnets very often. In addition, we're going to have over here where the checkboxes are, we're actually going to mount the same file system across both availability zones with our Amazon EC2 instances, so they can actually have, for example, the same HTML or the same app deployment directory. And that's all going to live in this thing that's at the very end, EFS, which is distributing mount points out to these little folders that live in the availability zones. There's other things here, like, there should be, for example, a cloud, like CloudWatch will probably be monitoring. Systems Manager will probably be managing stuff. You'll turn on AWS Config and AWS CloudTrail, along with other security services, right? And by the way, this is all living inside of availability zones that are inside of regions. And these subnets, notice that there's a data subnet, an app subnet, and a public subnet. They all live in these availability zones inside of the VPC. So you don't need to know everything I just said right now, because actually I didn't even mention S3, which is down here hosting static assets, right? But you don't need to know everything I know, but this is like what we're building towards. We are building towards this diagram for the remainder of class. Questions, concerns? Does everything make sense here? Does anyone see any, by the way, is anyone seeing any of this for the first time? Are there any services here that you haven't heard of before? If so, I'm very interested.
The memcache and EFS.
Memcache and EFS. Okay, good. So the Elasticache stuff and the EFS stuff. Good. Good. Anybody else?
I'll second the memcache.
Yeah, memcache doesn't actually get a lot of press, but it's a great service, especially when you have complex joins queries on the back end. It's great for caching data. Anybody else first time seeing the service?
Also memcache.
Okay. Good. Notice that there's no. Sorry, go ahead. What were you saying, Lucas?
Sorry, it was just I was also going to say memcache.
Okay. But the rest of this, you're like, oh, I'm kind of familiar with this. We will obviously cover other services like DynamoDB, and there's no containers, there's no serverless here. But this is the basic kind of architectural diagram. that includes auto scaling and application load balancing. Okay. All right. All right, so that's the end of our first section. Okay. Oh, we have a quick lab. All right, so this is a good time to mention is that for the duration of our class, we will actually be logged into something called webage.quicklabs.com. You ideally should have gotten an email that said, hey, you're enrolled in a class. And if you go to webage.quicklabs.com, first of all, you need to verify your email address. But if you don't know, by the way, if you're like, I don't know if I got that email, you should have gotten the email. So make sure you search for Quick Labs. And then you are enrolled, all of you, with your email addresses. It looks like one of you used your Gmail address. And that's fine, totally fine. Just make sure that when you go to, if you decide to recover your password, because you don't have the original email for whatever reason, make sure that you are logging in with that email address, because that's what we submitted into the system. And Mr. Verma didn't make it. Okay, so once you get logged in, yours will look a little bit different from mine. You'll probably like have a classroom or upcoming session or some variation thereof. But we're doing architecting on AWS. And so just know that when I start a slide that has this little like Quick Labs thing in the lower left-hand side, that means that we're probably going to do a lab for that particular time period. And so I typically will come in and pre-warm the labs so that they'll run. Please do not come in and start them early. They have a timer. And when that timer expires, the lab will delete itself. So please wait until we get to the lab area, unless you're going to do the lab, and then just go ahead and do the lab. And you can run the labs many times. So it's not like you only have to run it once. I did go in and opened up all the labs if you'd like to take a shot at them early. Not everybody does that, but they are open in case you want to. And so for the time being, just know that we're going to come back to this at the end of this particular slide lecture so that we can actually do the actual lab in question. So this is where we'll be, is webage.quicklabs.com. And so if you can't log in right now or whatnot, don't worry about it. There'll be time at the beginning of the actual official lab time. Okay. So let's start with the simplest piece of our architecture that we were looking at earlier, which is namely static assets, which is in the lower left-hand side. An S3 bucket, right? S3 is really well known, right? It's simple, it's easy. Everybody knows what S3 is, right? Well, here's the need. So you've just started up and you need a simple way to distribute, store, and analyze data reliably in the cloud. Basically, what S3 solves is S3 solves the problem of I have an unknown and unlimited set of data. It's a lot of different files. I don't need acidity or transactionalness. I just need a place to dump a bunch of files. It could be log files, it could be data files of whatever type, it could be behavioral analytics, it could be images, it could be videos. I need a place to distribute, store, and put a bunch of data. And I don't want to worry about like it being attached to a virtual machine. I want it to just sit in a repository somewhere that I can actually put. And in some cases, I want it to be web enabled. And I want it to be structured via buckets. And I want different tiers of storage as well, because some of the storage I'm going to hold on to for like 3 years. I'm not even going to really look at it, but I've got it for compliance reasons. Other pieces of storage, I want it to be hot because I'm going to be doing constant analytics and analysis against it. So this is where S3 comes in. So S3 is basically an API object storage system. So this is not a system that you're going to mount in an operating system. So this is not mountable. This is not block storage, right? Think of this as more like almost like an FTP server, which I found out there's actually a bunch of people still using FTP servers. I thought the FTP servers is kind of retired, but they're actually still kicking around, actually. And a lot of people are using them for data transfer. So S3 is designed for 11 nines of durability, and it can actually call other AWS services based on things that happen to the bucket. So for example, if you put a file into a bucket, you can actually trigger a Lambda function to either do a video conversion or create a notification of some type. And of course, as you well know, once an event triggers into Lambda, you can pretty much hit any AWS service you want at that point. Like it's game over. By the way, just as a side note, S3 actually can act as an FTP server. There's actually an FTP service where S3 is on the back end, and it's a secure FTP service. Amazon just released that, I think, within the last 2 years. So just FYI, in case you're looking for secure FTP. So S3, by the way, will help you to store and distribute static web content and media. And you might say, Michael, why do I care about that? Because you don't want your web servers doing that. That's a waste of their processing power. Feeding out files is something that S3 does with almost like limited to no cost. It'll scale indefinitely, at least for our use cases. And you don't need to have your web server spending compute, network, and memory cycles distributing files. That's not, you want your dynamic content on the web server because that's primarily where you gain the most efficiency. So this is one of those performance efficiency challenges where let's just put our static web content and media, let's just put it out on an S3. And by the way, it can have a domain name. So it could be images.yourspecialdomainname.com. And then that way you can just have your web page call that other domain name when it loads, and it'll still be branded like as if it was your site. But it now offloads all that responsibility on something else. Now, S3 is interesting because if we go into the console for just a second, let's say that I'm moving off of S3. What happens is that this is the dashboard for S3. And when you come in here and create a bucket, just remember that bucket names are globally unique, right? So if I create a test bucket, it's got to have some level of randomness to it. Otherwise, you'll get an error saying, hey, bucket name's already taken. You do have to pick kind of a home region for your buckets. So in this case, if I put it in US East 2, and I can copy settings from an existing bucket. One thing I want to note is that by default, everything in AWS, when you launch it, the internet is restricted from getting to it. So this includes the firewalls for security groups. This includes obviously S3 buckets, but you have to uncheck a bunch of boxes in order to make your stuff publicly available. And those kind of misconfigurations are what shows up in the news, right? So like, you hear like people leaving social security numbers and whatnot available. So notice this says block all public access. You can also turn on versioning, which allows you to keep a copy of every changed file in an S3 bucket. You can also tag it. You can turn on encryption. And there's other advanced settings, like you can actually enable what's called an object lock. It's almost like a compliance lock, which will allow you to write the file once, but nobody can change it, which means it cannot be overwritten or deleted, actually. And when you do this, by the way, it will allow all objects in this bucket to be locked. And so at the time the object is copied up, you can specify the kind of lock that you want. And then you can just come in here and you can create the bucket. And the next thing you know, we come down to tests, right? Here's our test bucket. The objects are not public. It's rooted in Ohio. And notice from here, I can just upload whatever files I want. So I can either drag or drop, or I can add a file or a folder. And then everything I put in here, by the way, let's say I had a file and we can use the student roster. That's not going to give anything away. And let's say I upload that, and then I can actually set permissions at the time. So I can like keep it private or grant public read access, or I can actually specify things like storage classes. S3 has a ridiculous number of hot to cold storage classes that I can use. And I want you to ignore intelligent tiering for a moment. But I can reduce from hot storage to less hot, which is just standard and frequent access, to less redundant, cooler storage. And that can get into Glacier and then Glacier Deep Archive. By the way, there is reduced redundancy storage here. Most people don't use it because it's the older, right? But as you go down this tier, by the way, the storage gets cheaper. Intelligent tiering is a little different because intelligent tiering storage is machine, like algorithmically driven storage that will determine your access pattern, and it will move you to hotter or colder storage with no charge to you, just based on like you saying, hey, I want you to turn on intelligent tiering. So intelligent tiering is for when you put data in S3 and you don't know what the access pattern is going to be. So you don't know whether you want it to be hot or cold, but you want it to actually go down to colder storage so you can save money if it's not being accessed. In this way, you don't have to set up lifecycle policies, right? The lifecycle policies in this particular case are then done for you, right? Notice also that when I upload the object, I can actually specify server-side encryption with a key, and I can add additional metadata if I want to the system. But that's S3, right? I upload the file, I just hit go, upload, and then what will happen is that it'll succeed in the upload. And then from there, I can actually go in and configure additional object permissions if I want to. Look at all the different versions, right? So there's the current version. If I upload a different modification, then it will increment a version. There'll be another version there. And then I can see the owner, the object permissions, authenticated groups, and then any properties. Notice that this now has a URL, and watch this. No one can get to it. So by default, when you upload objects, you are denied access to those objects. But I could see it if I maybe I want to open this up, right, and give it up to everybody. No, I'm not going to do that since it does have our information in it. But note that this object could be made public with just a few clicks. So I'm going to delete this just for consistency's sake. Any questions? Okay. Access control, by the way, by default is locked down. You obviously can make it public. You saw me do that. You can also create access policies. Generally, they ask that you create IAM access policies, which is basically user-based policies, or you can actually create bucket policies, which is where the resource grants access to various IDs. It is recommended that you don't use this. There's an antiquated system called access control lists. They're basically ACL policies. They ask that you don't use those anymore. They're trying to retire those. S3 predates users inside of AWS because there used to not be an account management system. So the access control policies, they actually ask that you kind of hold off on using. Here, by the way, is a bucket policy, not an access control list, but bucket policy. So you're doing access control through a bucket. And what this does is this says, you know what, I'm going to deny anybody from doing anything against S3, against this particular example bucket, unless they're coming from this IP address. In other words, if they're coming from this IP address, I want you to allow them. In other words, the deny doesn't apply. And that's a bucket policy. Now, if you specify an IAM user, you can just grant the IAM user access to the bucket. By the way, just know that by default, IAM will deny access to everything implicitly. So you do not have access to anything inside of AWS once you get a username unless someone expressly grants you access. So this alone would not grant you access since this is a deny policy. You'd actually have to have another policy that says I allow, right? Now, you can create access points that are unique host names with dedicated access policies that describe how data can be accessed using that endpoint. These points can support a single user. They can support applications or groups of users. But basically, you can create an alias. An access point is an alias with a unique host name with a discrete set of security policies that can access an S3 bucket. So just know that you can actually put like aliases, if you will, on your S3 buckets if you need them. The other use case for S3 is that you can actually host an entire static website inside of an S3 bucket. It does have to be named after the domain in question, and you'll have to do a little bit like verification that you own the domain. But then what will happen is that you can put images, videos, client-side scripts, HTML files in there, and it will actually load up. And that's a great use case for S3. If you don't want to like host your own static website, you can just actually have S3 do it. No servers involved, and it's incredibly performant. Versioning, as you saw before, like for example, if we go back to our bucket, and let's say that I want to upload yet another object. So what I can do is I can actually go back. What's going on with my bucket here? Let's go back to our test bucket. Let's say I come up here and I want to go ahead and upload that file again, right? Because that file, for whatever reason, I didn't necessarily want to delete it. And I actually do want versioning enabled on it. So, but I'm sorry, I've got versioning enabled on the bucket. So it'll automatically inherit versioning. And then I can upload this file. And then what I can do is I could come up here and let's say that I want to make just a quick change. And I save it and I come out here and you know what? I actually want an upload a new version of this file. And so what I can do is I can upload the file again. And let's see what happened with my versions for this file. Notice that when I deleted it, it created the delete marker. Then I re-added it, and then I added it again. And so notice that the deletion was actually just another version of the file. And I added yet another version and another version. Now, programmatically, you can access these files, but if I click into this one, I can actually get this file if I need to. And I could download it if I wanted to. And if I needed a specific URL to access it, it's not going to be accessible. But notice that that's the core link. That actually leads me to the current version. If I want the version that I was just looking at, I'm going to have to pull that down from programmatically. And that's versioning. So note that even a deletion is actually a marker in a version. By the way, once versioning is enabled, you can suspend versioning, but for some reason you can't remove it. So the bucket will always be marked as once being versioned, but now no longer versioned, right? So I find that to be interesting. Okay, the other thing to think about is that you do want to make sure that if you make it available publicly, that you actually do some cross-origin resource sharing, that you actually specify who can pull from your bucket if you make the bucket public. In other words, if they're coming from this domain, can they put, post, and delete stuff? And if so, how is that allowed? And so make sure that you're considering that if you're coming from another domain, you're considering your core's configuration if you are doing any kind of cross-domain items. The third use case is as a data store for algorithmic computation, large-scale analytics, right? This is a common use case, right? This could be everything from machine learning to clickstream to media transcoding. Anything large-scale computational involving a large set of files is an excellent use case for S3. And then the last use case that makes sense is has a backup tool, like people put their backups, and you can actually use S3 with a proxy called the storage gateway to actually extend your tape libraries, your file systems, and even your network disks. You can actually have a proxy in your data center, and it will store all that data as a backup in S3 or in Glacier if it's a tape drive. So you can actually extend your data center storage into AWS using what's called the storage gateway, and it will use S3 and Glacier as its backend, which is pretty awesome. Now, there's 3 ways to access any service inside of AWS, and they all center around the API. Because you might remember at the beginning, I said that everything is software defined, which means it's all API driven. All of AWS's infrastructure is API driven. There's 3 ways to manage the API. There's through the web console, which you just saw. There is through the CLI, which there's a, I should blow that up. So there's the command line interface is officially published by AWS, and there's actually an AWS command line tool, and it's called AWS. And AWS will allow you to access any of the services. So notice there's a list of services here: Athena, AppSync, AppMesh, CloudFront. You'll see there. And so, like for example, if I want to list all of the instances that I have inside of US East 2, I can actually describe them, and I can get everything from private IP addresses to owner ID to network interfaces, even the hypervisor. Notice it says the hypervisor. They're using a version of Zen. Any attached disks. Now notice, you may remember before that I didn't actually have any systems in US East 1. So if I do that for US East 1, which is Virginia, notice that nothing comes back. But if I go back to 2, then it gives me all the YAML. This command line tool, by the way, when you install it, like I'm on Windows right now, but you can run this brew install AWS CLI if you're on Mac. If you're on Windows and you have Chocolatey, you can do Choco install AWS CLI. You can download it, install it yourself. Do note that when you first get this, you want to run AWS configure. It's going to ask you questions like it wants your access key and secret key, wants your default region name, which we just talked about regions, and it's going to want your output format. As of the latest version of the AWS CLI, it supports YAML. So you can actually specify JSON, or if you just want text, you can do that as well. But that's the second way. This is the CLI. The other way is to do it programmatically, like using an SDK, which I'm not going to show you because that's a little bit more involved. But like if you're using Terraform, Terraform, for example, uses the SDK to interact with AWS. Terraform is a third-party tool that does provisioning for cloud providers, and it is cloud agnostic. So I use Terraform quite a bit, actually. Okay, good. Yeah, everything's good. All right. So 3 ways: console, CLI, or software development kits, which are basically libraries you import into your program in your favorite language: Python, .NET, Java. There are tons of SDKs out there. So this is how you can actually submit files into S3. By the way, you can also parallelize large S3 uploads. By the way, this is on the exam. Does anyone know what the largest single file size can be for an object on S3? What's the single largest file you can have on S3? Anyone know? It's 5 terabytes, actually. So you can break anything above 100 megabytes up into a multi-part upload. What will happen is each individual part is actually copied up to AWS, and it will hold on to the parts until the last part is there, and then it will reassemble everything. So multi-part upload is excellent because it'll allow you to split a file up into different pieces, upload them in parallel, and it will hold on to all the parts until it's got all of them, and then reassemble them and then put them in your bucket. So multi-part upload can be engaged when you do the upload through the AWS CLI or through the SDK. So I want to stop here for just a second because we've been going for about 90 minutes, and I know that we're in the middle of a topic, but I want to make sure that we just take a very short break to give your brain a refresh before we walk through the rest of the S3 components and then roll into a lab. So I want to just go ahead and just take a short 10-minute break. It's actually 10:05 by my clock right now. Let's come back in 10 minutes and continue this discussion. So everyone take away from your computer, grab some water, take a bio break, and we'll resume in exactly 10 minutes, so 10:15, okay? So see you in just a bit. All right, everyone. Welcome back. Thank you for indulging me. I might have had a small crisis with a teenager that just happened to coincide with break time, so that worked out very well. One of the interesting things about teaching from home is all the now daily interactions with family and pets and whatnot that happen. Things that would still happen if you weren't there. Well, although I imagine he would be at school also. So anyway, questions, curiosities, or anything else that kind of popped up, or anything that you like, for example, you didn't know or hadn't encountered before. Like most people don't know about multi-part upload. We're necessarily aware of that. Most people haven't used versioning. So you guys got curious. Anything we've covered thus far that's like brand new to people? Okay. Well, we're going to move through the rest of the material, and then we're going to roll into a lab. So let's talk about transfer acceleration. So transfer acceleration is basically, instead of running from the end user and copying a file from their browser or location, wherever, over to the S3 bucket, let's say in this case, US East 2 Ohio. What will happen is that if you enable transfer acceleration for a bucket, it will instead actually go to a CloudFront edge location. So one of those edge locations that we were talking about before, that was one of the two places, really three places, that you can actually have your data cached or pushed to. And what happens is that instead of going all the way out to Virginia to that endpoint, if I was in Atlanta, for example, there's a server in Atlanta, a CloudFront server, I'd actually go to that server, and then across Amazon's dedicated high-speed backbone, that server would act as a proxy to push my file into the S3 bucket. And so transfer acceleration is a way for you to leverage AWS's distributed edge servers to speed your transfers. So instead of running across the internet, you're running across their high-speed backbone. Again, that happens invisibly and automatically to you. When you enable transfer acceleration, DNS for the actual bucket redirects to a CloudFront server. And since AWS controls that, they can turn it off and on pretty easily. And that will direct you to the nearest edge location. So if you're in Ohio and there's an edge server up there, you'll go to that edge server. If you're in California and there's an edge server over there, you'll go to the California edge server. So you go to the nearest, fastest edge server that's available to you to continue your transfer. And so that's transfer acceleration. Other ways to move data into S3 would be, for example, actually getting a device called Snowball, of which there's a storage and a compute optimized version now. But the Snowball is actually an 80 terabyte transfer device. It actually hooks in through Ethernet, right, into your network. And there are options for other connectors if you need to. But basically, whether you get the small little gray box, which is 80 terabytes, or the basically petabyte scale data transport service, the Snowmobile, which I think was released in 2016. Oh yeah, it was 2016 because I was actually there when they drove the truck up on the stage, which just cracked me up. And then they put it in the exhibition hall. But basically, this hooks up, I think, through a variety of fiber connections to your data center and allows you to just push data to it. And then it has a little security kind of attaché to it, and they and the truck drive back to Amazon, and the data is extracted out and then put into your S3 buckets. So whether you use a Snowball or a Snowmobile, there are ways to transfer data beyond the network connection, especially if you need faster data transfer. Snowball can take days, like a week to turn around. Snowmobile takes a little bit longer, 2 or 3 weeks. So you should use Amazon S3 when you have a broad data set, like log files, whatever, distributed, and you're going to have variable access, and you've got a large number of users like spread across, especially if they're web enabled, that need to access those files and content. It's really excellent for, like, I need to put this file here, and then I'll let a lot of people read it, right? So it's great for that. Not great for transactional workloads. It doesn't in and of itself do analytics, though it can be a great data source for analytics. There are things like Athena and Redshift and other analytics tools that will actually hook into S3. So it's kind of a great kind of place to put your data if you want to enable access for anything else, users, analytics systems, whatever. So S3 is just a great like data repository. It's not great. You can't mount this inside a file system, so it's not really good for that. Like you can't use it for block storage. If you've got data that's changing a lot and you need like sub millisecond response times, you want to put that in DynamoDB or some other data service. And then there's a variant of S3 that's great for archival storage, but S3 standard is not awesome for archival storage. If you want to do that, then you want to go for a lower, like a colder tier of storage, like Glacier or Glacier Deep Dive, which are built for archival and compliance storage. Now, S3 costing has a couple of different dimensions to it, but it's basically the size of the files that you stick in the bucket, whether you've pulled a lot of data out, because Amazon will let you put data in all day long. And this is part of cost optimizations. Amazon will allow you to put data in for free, but when you pull data out, it will start charging you. There's ways to get around that to a certain degree. Like if you pull the CloudFront, for example, they won't charge you for pulling data out, but they will charge you for data being pulled from CloudFront, which in some cases is actually cheaper. And then if you make a lot of changes to files, like put copies, post, lists, and gets, then that's, gets not so much, but like the rest of them are going to cost you. When you do a lot of manipulations of data, it's going to cost you something. If you ever, by the way, need to get a little bit more precise with your estimations, there is this tool. Oh, let me actually delete this. Actually, I will do that in just a second. Let me stay focused on this. There's actually a tool called the Simple Monthly Calculator. And the AWS Simple Monthly Calculator is a calculator that they've been trying to retire it for a while, but people just love it so much. But this calculator, which I'm going to post in the chat, will allow you to do some forecasting against core services. And notice there's a bunch of services over here on the left-hand side. But what this does is that, let's say we're looking at Amazon S3, and we want to put a terabyte of data out there, and the data itself is relatively static. So it's only 100 files, and we're only going to do like 10 times the verification. Notice that cost me $23 for a terabyte of the hottest storage you can get on S3. Notice that if I add more read requests to the system, it doesn't actually go up that much. But if I put in a bunch of changes, equivalent, it goes up by a couple of dollars, which is very different than the couple of cents that it went up when I was just reading. So just note, and by the way, if I change that to a petabyte, notice that it's going to be a lot more, right? So I'm going to $24,000 a month. I've had, the largest company I ever worked for had 5.6 petabytes of information inside of AWS, and I think we were paying a lot. I don't know if it was this much though. That sounds about right, actually. Yeah, close to $150,000 for that much. So, by the way, at the time they didn't have great tiering options, so they had Glacier and that was it. So we were pretty much running hot storage the entire time. We didn't have any colder storage to step down to at that particular point in time. But for the most part, this is going to be enterprise class storage. But this simple monthly calculator will allow you to calculate costs for EC2, for CloudFront, and for RDS. And you can see all the services on the left-hand side, right? WorkDocs, Redshift, Glacier, SQS, et cetera, et cetera, et cetera. There are more services. You just have to choose them. By the way, this will take you to the other tool that I'm going to recommend, which is called calculator.aws. Between the two of them, they kind of cover all the services, but calculator.aws is cool because you can actually create estimates. So if we were doing S3 over here, we could actually configure our different zones all in one fell swoop, specify the amount, gigabytes per month, the amount of storage, all the puts, gets and all that. And then any data transfer that we expect against that system. And then we could actually just add this to our estimate. And then you can create a full list of services with a full estimation. So calculator.aws doesn't have all the services yet, but it has most of them. And so, and you can actually create varying estimates. So you can actually name your estimate when you save it, create a bunch of different estimates for different projects. So calculator.aws, which I just posted in chat, is another great link for cost estimation, along with the simple monthly calculator. The simple monthly calculator will be retired at some point in time, but it's quicker and easier to use than the current calculator.aws is. Questions, comments, curiosities? Okay. Do note that transfer into Amazon you don't have to pay for, or transfer out to CloudFront or to EC2 in the same region they typically don't charge you for. But then we have to talk about Glacier, because that's like the coldest form of storage, Glacier and Glacier Deep Archive. And this is for long-term storage. This is very different than S3. S3, the file is available, so you can actually hit it and pull it off of a URL or pull it out of the bucket if you want to. Glacier, it's in a vault, so you can't actually get to it until you restore it, right? This is 1/6 typically and 1/10 in my own like unprofessional estimation of doing costs. It's usually a fraction of the cost of what standard S3 costs. Let's take a look at that. Let's challenge that a little bit, right? So here we are in S3, and I put 5.6 petabytes in, and that was $131,000, right? If I were to switch that and put this into Glacier instead, let's say I put 5.6 petabytes into Glacier, and I only did like standard retrieval. Let's say I retrieve, let's say 1,000, terabyte per month, because for the most part this is archival compliance, and I'm not making any changes to this data, right? Notice that the cost here is only $25,000, so it's practically like 1/5, 1/6 of the cost. If I go even colder from Glacier and I go down to Deep Archive, if I do 5.6 petabytes here, and let's say I do the same standard retrieval of about a terabyte. Oh, I could just put a terabyte. Notice that it's now even less. So we were originally at 131,000 and change. Then we were at basically 25,000 and change for Glacier. And notice that Deep Archive is even colder than Glacier, right? So it's literally 1/4 of what Glacier costs. But by the way, when you stick stuff in Deep Archive, it has to stay there for 6 months before you even think about pulling it out. So this really is for long-term archival storage, way colder. But those are the different storage tiers. Now, with Glacier and its variant Deep Archive, what happens is everything goes into a vault. So you've got archives that go into a vault, right? And those archives, by the way, can be sizable. I think 20 terabytes is the limit, right, for a single archive. That one I may be misquoting, so I'll have to look that up to confirm it. But then what happens is that when you want to get that data back, you kick off a standard retrieval request. And what happens is that archive is pulled out, and that doesn't even start for 3 to 5 hours. And then in 3 to 5 hours, it starts the restore process and then puts it into S3 so that you can retrieve it. Now you can expedite that and say, I want to do it right now, and you pay like pennies on the dollar, right? It's like something really tiny. Or you can bulk retrieve, which takes about somewhere between 5 and 12 hours to start. Whereas the expedited retrieval, if you pay for that, there's a little fee associated with it. I think it takes like 5 minutes for it to start. But standard retrieval takes 3 to 5 hours. Bulk retrieval takes 5 to 12. So by the way, this shows up sometimes on the exam. It's like, what is the time? Standard retrieval is 3 to 5 hours before it starts the restore process. Bulk retrieval is 5 to 12 hours. Expedited is like 1 to 5 minutes in there. Otherwise, your data is hidden away. You've got a reference to it, but you can't get to it. And once it's restored, again, it goes back to S3. Now you've got S3 standard. You've got S3 standard infrequent access, which, by the way, when you put a file there, it has to stay there for 30 days. One zone infrequent access, which is like reduced availability storage, but not really, because the numbers haven't really changed. Amazon says it's the same. but you're in one zone. But there is a reduced redundancy, so I'm not sure why the documents aren't reflecting that. But that's even cheaper, right? And that also has to stay there for 30 days. And then there's Glacier and then Deep Archive. And Deep Archive files have to stay there for 180 days. So basically 6 months or so. Glacier, that doesn't really have restrictions. Your data is just not accessible, right? So when you think about hot to cold, S3 standard is for hot access, constantly looked at data. S3 standard, like infrequent access, is for data that's occasionally accessed. It's long lived, but it's kind of infrequently accessed. Same for one zone. And then Glacier and Deep Archive is like, this is rarely touched. That you might ask for this once a year, right? That's rarely accessed data. And then the intelligent tiering tier is the one that will move it between all the hot and cold tiers based on your access pattern. And by the way, if it makes a mistake and moves stuff into Glacier that then gets accessed and it has to expedite and restore it, you don't pay the fee for that. That's all included in your intelligent tiering costs. So it will move objects based on access patterns to different tiers of storage. Now, Amazon will allow you with S3 to create lifecycle policy that says, look, after this many days, I want you to move it to this colder tier of storage. After 60 days, I want you to move it down to Glacier. And then, after a year, just delete it. Let it go. We did this when I ran a video company where people would upload videos, and in the first 30 days, that video was hit pretty heavy. After the first 30 days, videos were accessed infrequently for about a year. And then after a year, we would just delete them because we didn't need to hold on to them. We weren't required to keep the videos. So you can create lifecycle policies that actually move objects around. Does anyone have any questions about lifecycle policies, S3 intelligent tiering, storage classes, multi-part uploads, transfer acceleration? Anyone have any questions about any of the S3 topics that we just covered?
What was the time limit for expedite retrieval, standard and bulk retrieval? I missed that noting in there. No.
Yeah, so expedited retrieval usually takes 1 to 5 minutes. Standard retrieval takes 3 to 5 hours, and bulk retrieval takes 5 to 12 hours to start the restore process. So notice that this isn't restore duration; it's just to start the restore process.
Okay.
Because the restore duration actually depends on the size of the object that you're restoring.
Mm-hmm. Thank you.
Yeah. Other questions? Okay. Other questions that arise is how do we choose regions for our architecture, right? Because really the first consideration when we're trying to figure out like where things need to live inside of AWS is one, do we have a legal like data residency and regulatory compliance? Like for example, since you work for Booz, predominantly people are like, especially if it's a government affiliated agency, most of your stuff is going to end up in GovCloud, East or West, right? But it might be like, well, we are using the public sector and we're affiliated, but we don't need GovCloud restriction, level of protection. So let's actually just go into Virginia, right? Because that's our closest data center. Or we're located a little bit north and we're okay using Ohio, right? So just note that obviously data residency and regulatory compliance, like if there's a legal compliance, that's usually the first thing for choosing a region. The second reason is how close are we to our users? Like for example, when I was just talking about Virginia, we chose Virginia because maybe their office is located in Virginia, so most of their customers are in Virginia, right? And so typically you choose regions that are closest to your users. This, by the way, is why they created local zones. Because local zone is just an availability zone that's closer to the users that are in Boston, Miami, and Houston. So Amazon says, choose basically the region and subsequently the availability zone that's closest to your user. Now, with most availability zones, it doesn't matter which of the 6 zones you choose in Virginia. They're all going to be fast to your users in Virginia. But if you have to choose a local zone because you want to be closer to users in Boston or closer to Miami or closer to Houston, you can do that, right? So proximity of users to the services or data in question is probably the second reason as to why, how, who, what you choose a region. The third is the service I'm looking for available in the region in question? Predominantly new services go into Virginia and or Oregon first. They don't go into, Ohio or Canada or Mumbai or, Spain. They don't go there first, right? They go either where Amazon lives or their first data center, because Virginia was the first data center Amazon had. By the way, what if you wanted to look up and see if something was available, I don't know, in GovCloud, right? Well, the cool thing is that there's this thing called a AWS service region map by region. Yeah, change the name. So if you wanted to see like, oh, I'm kind of curious as to what services are available, what can happen is you can actually come into your data center and say, you know what, we really want to use Bracket. Bracket, by the way, it's kind of a joke, is a quantum computing service. So if I was in Ohio, notice that Bracket isn't listed here. But if I switch over to, say, Virginia, I'm making a guess here, by the way, I still don't see Bracket. Where is Bracket actually located? Well, I would suspect that if it's not in Virginia, what's the other place it's going to be if it's not in Virginia?
Oregon.
Oregon, right? So let's take a look and see if it's in Oregon. There it is. There's Bracket, right? So Bracket is the quantum computing service, and it's available only in Oregon, nowhere else. Now, for most of the Boost employees, I say us Boost employees, I don't work for Boost, although I do a lot of work for them, is that you're going to be either in GovCloud East or GovCloud West if you're dealing with those particular aspects. And so I will say that, by the way, GovCloud is very much caught up with things like Kubernetes, containers, container registry, container service. What else? Is Proton out here? No, Proton's not out here. No one, it's okay. You don't need Proton. What's another service that's kind of been released recently? Amplify? Nope, Amplify's not out there. But like Fargate's out there. So most of the core services are available in GovCloud, but you want to check. Just because Amazon announces something as the latest and greatest doesn't mean it's available in GovCloud just yet. It's typically available in Oregon or Virginia. I post this out. This is the service region map. You definitely want to hold on to this, or at least just know that you need to type in AWS service region map. That's why, by the way, you see me typing it into Google, is because the links, they rarely like retire, but like in case you need to find something, you can just like type it in, right, and get the official AWS link. All right. So the first, what's the first reason that you would choose a region? What's the first like primary region? Because it's not proximity users. It's not service feature and availability. What's the first reason that people typically choose a region?
Whether it covers the service which I want to use.
Well, that's the one that we just went over. What was the one that we went over 2 slides ago? What was the first reason most people choose a region? So to say it's usually because, sorry, say again.
East 1.
Well, US East 1 is Virginia, right? And that's primarily where service availability exists. But the main reason people, like the first reason people choose a region is because of regulatory compliances. That's the first reason someone will choose a region. I can't actually go into, for example, the EU because I work for companies that require us to stay on US soil, right? And so therefore that might be a regulatory compliance, right? And so that's the first reason. The second reason is proximity to users, and the third is service availability. Now, I disagree with this being listed last, so I don't think these are necessarily listed in any particular order. But the other one is cost effectiveness. Yeah, no worries. The worst is cost effectiveness. Like for example, earlier when we were doing our costing estimation with the simple monthly calculator, let me close this out. If we go back to the simple monthly calculator, and let's say Stephen comes back to me and says, you know what, Michael, I want to run a system and I want to run it in Northern Virginia. And you know what? Let's just do a T3 2X large. That's not a bad system. That's good, right? He's like, that's a 2x8 or a 2x16 box. And our current bill is $243. By the way, to get a server at a 2x16, 2 processors and 16 gigs of RAM that has 5 gigabits of backplane access to the network, like to the internet, that's pretty good, actually. That's $250 a month with tax. Now, notice I'm in Virginia. Now, if I decide, if Steven comes back to me and says, you know what? Oh, by the way, look at these other zones. The local zones are here: Boston, Houston, Miami. Right? Let's say that Steven comes back to me and says, you know what? I need to switch it to Oregon. And so let's make this like run in Oregon instead. It's like, okay. Well, we need to switch back, by the way, and remove Virginia. It's still there in our estimate. But if we go back to Oregon, we're now back to $243, right? And that's the same price for the most part. Now, let's say we remove this and we're back to 0, and someone says, you know what? I really want to run that box in Northern California because that's where our users are at. What just happened? What's the difference? How much more is that compared to where we were in Oregon and Virginia? What's the cost differential between what we were just looking at and that number right there, the 290.46? So we were at 243, and now all of a sudden, $47 later in California, I'm now paying $290 for the same box. I'm paying $290 for the same box. So $47. So I just went up 20% just to be in Northern California. So that's the fourth reason, by the way, is cost effectiveness, is that every single region in like in the EU and in like the Asia Pacific, there's regions that are more expensive than the other regions. Let me show you another example. So let's say we remove Northern California because we're like, no, that's not going to work. But we go over and we're saying, you know what? I want to do the same thing in Sydney. And Sydney's like, it's going to cost you $309. You're like, that's more expensive than the United States, but that's okay. It's Sydney, right? So 309, and then we switch over to Tokyo and we run that same box. It's a little bit more, right? Now in this case, it's only $9 more, so it's not a vast difference. But just be aware that boxes do cost different prices in different locations. In Singapore, for example, that same box is going to match Sydney's price, but Tokyo is typically considered a more expensive location to run servers in. Let's pick one more. Not Osaka. Actually, let's pick Hong Kong. Notice in Hong Kong, running the same box, we went from 309 to 342, right? So, be mindful that it is going to cost different things. Do you absolutely need to be in Hong Kong? Or could you be in Singapore or Seoul or Sydney and still be able to provide a good user experience for your users? If the answer is no, then go pay the Hong Kong price. But otherwise, pull it out somewhere else and use CloudFront, right, to distribute instead. So 4 kind of choices when choosing a region. Do you have a legal compliance? How close is this to my users? Is the service available that I'm looking for? And what's the cost differential, right? Something to consider. All right, any questions about choosing a region? Okay, whoop, whoop, gotta do a little dance because we're done with our third module. And so now what we're gonna do is we're gonna spend some time, and oddly enough, they only allocate 20 minutes for this. So, make sure that when we get in here, we stay focused. I'm like 20 minutes. So we're gonna host a static website. Now, the problem you're solving is you want to host a static website, but you don't want to host servers, right? So we're just going to use S3. You're going to create a bucket, deploy a website into that bucket, make that website publicly available, right? That's it. That's the whole lab. Now here's how we're going to start. We're going to close out all the regional services and stuff. What we're going to do is we're going to go to WebAge, You're going to log in to webage.quicklabs.com, and I'm going to post that link again just to make sure you have it. You're going to log in with the email address that you use to register for class. And by the way, typically the password is WAS admin. If that doesn't work, just click on forgot password and have it email you the password to your account. Is there anybody, by the way, at this point who is not logged into their system?
I'm not, it didn't like that admin password. So
So you did forgot password. Okay. And I'm sorry, who was that talking? Was that Steven? Sean. Sorry, sure, Sean. All right. And let's see, Sean, just to make sure. Hello. Let's see. Yeah, you use your BAH email address, so you should be good. Okay. So once you get in to the classroom architecting, which will be there'll be a little option on the left hand side of like classes and labs, and it's already been pre-warmed and it's already open. So once you open the lab, what's going to happen is you're going to see this page right here. You're going to click the start button. That's going to start a timer. And by the way, it's going to open up a bunch of information like opening a console. So when you open the console, it's actually going to log you into an AWS account that's just for you. And you're going to be in a region called US West 2. Please do not change that region in the upper right-hand side. Stay in US West 2. And then all you're going to do from there is you're going to follow the directions. So on the right-hand side, you'll see that there's task 1, there's task 2, there's task 3, and task 4. That's it. And you're going to follow the directions. So turn on your detail orientation. Because if you miss a step, it's going to cause failure later on. So make sure that you follow the steps as they're delineated. If for some reason you run into a problem, I am right here. You let me know. I'm not going anywhere. And I will help you troubleshoot whatever the issue is. But typically, it's because there was a step missed before. Okay? So that's what we're doing right now. We're going to take at least 20 minutes. We're going to go through the lab. So go forth and conquer. I'm going to be right here. I'm going to go on mute. If you have any questions at all about anything, not just the lab, let me know. Otherwise, let's get it. Everyone good?
So I logged in and I reset my password. So what I missed that part while I was doing it. So I had to go to the lab or something.
Yeah. So do me a favor if you don't mind. Share your screen for me, Sandeep,
Sure.
because this would be great for everybody to see.
Yeah.
Welcome back, everybody. It is a quarter after the hour, and we are moving on. Does anyone have any questions about hosting a static website, creating a bucket, any of those particular challenges that arose in the lab? Okay. Okay. Well, we've kind of set the foundation for talking about regions, availability zones, and local zones. And we're now moving into obviously object storage, which you talked about Glacier and the kind of cold and hot tiers of storage. Now, before lunch, because we are going to stop in about 45 minutes, we're going to talk about compute. All right, let's talk about compute. One of most people's favorite topics. If you're in the IT industry, is because we have to host apps, right? So we're going to talk about the compute layer. Let me share my screen so we can facilitate that. Amazon. Great. Sorry. All right. So let's talk about the compute layers. Now, there's 3 ways in the industry in general to host applications. You can do it in a virtual machine. You can do it in a container, which sits on top of a virtual machine, or physical host, right? Or you can do serverless, which also sits on top of virtual machine typically, but serverless just means hidden servers, so you don't see any of that, right? So virtual machines, containers, and then serverless are the orders of abstraction for how we typically host applications. Now that's true whether it's a database application, because you can run it in a virtual machine, you can run it in a container, you can actually have all that abstracted away. Or if it's like a web app or a microservice or a monolith, doesn't matter, right? It's either going to run in a virtual machine with an operating system, it's going to run in a container with process virtualization, or it's going to run in either one of those two, but it's going to be serverless, which means you don't manage the servers in any way, shape, or form, right? Those are the three layers, if you will. So let's talk about adding a compute layer. So as we look at our kind of original, like large scale diagram, right? What we're seeing is we've already set up our static assets and put them in an S3 bucket. So now our images, our JPEGs, our CSS files, our JavaScript, that's all moved off onto S3. But now we've got application concerns and maybe even some web hosting concerns that are dynamic. And we're going to run this on Amazon EC2, but we also want to share that amongst all of the web servers / app servers. So we want to share the same storage, so have them mount the same kind of source files, if you will, simultaneously. And that's where the EFS on the right-hand side comes in. It's because EFS provides network file storage that can be mounted across a bunch of different EC2 virtual machines. This is a network drive. It's not a local block attached storage, right? It's not direct attached. But EC2 is just a virtual machine service, so that's easy, right? So the need here is that you need to run applications that are going to be used by a consistent but small number of users. And so this is where EC2, the associated hard drives called EBS block storage comes in, as well as the different t-shirt sizes of virtual machines that you can get with AWS. Now, the great thing about the t-shirt sizes of virtual machines is that they are designed for either compute, memory, or general purpose, or they're designed for data, or they're designed for like GPU, like machine learning style access, right? And there's some test boxes in there as well, but we'll talk about all that. So let's talk about adding compute. So everybody at this day and age knows what a virtual machine is. We can run them locally, we run them in their data center, right? Basically, we're running any operating system. There's 3 operating systems as of 2021. AWS supports Linux, Windows, and Mac OS. Mac OS, by the way, is a relative new addition, but it's a first-class citizen, has all the full support of AWS. So you can run Mac boxes if you want to now. Now, why virtual machines? Well, this is software-defined infrastructure. So we're trying to get away from managing hardware, but we still need an operating system. This is where EC2 comes in, right? Now, in order to boot a virtual machine, you need to pick the operating system. That operating system image that we boot off of is called an AMI, or Amazon Machine Image. Now, if we go out to our browser for a second, ignoring my reading about real world containers, right? When we go over to EC2, we're going over to EC2 in the console, and I'm going to switch back to Ohio because that's where I was before. You know, we've already got one instance running in here, right? What kind of instance is this? Well, when I chose to boot this instance, I had to choose an AMI ID, and that's what this is. Right in the middle, you see that AMI ID? That's an ID for a particular flavor of operating system. In this case, it thinks the platform is Ubuntu. Is it Ubuntu? Probably is Ubuntu, actually. And it's Linux, Unix. And then, by the way, this is 1804, right? Because it actually says it in the AMI name, actually says it in the location. This is the Ubuntu official image. And if I click on that AMI ID, notice this ID right here, that will actually, oh, no. I'm not sure what's going on with my account. It would normally take you to a description of what the AMI actually is. But hold on just one second. Let's see if we can search by something else. Hello, I'm in AMIs, and I would like to, oh, let's look by public images. Oh, that's not gonna work. Okay, sorry, my demo is going horribly. Hold on one second. Instances, there's my instance ID. Let's copy this AMI ID and see if we can figure out what's going on. So I click on AMIs. If I do this, aha, there it is. It's under public images, which means that the vendor has made these images publicly available, right, for us to consume. There's also private images, which are ones that I have made or make. Now notice if I take the filter off, I don't have any current AMIs, not in US East 2. And then I have none that I've like owned or made that are like not shared between accounts, right? These, right now I have no AMIs in my system. Now I could come up here, by the way, to this instance, right click on it and say, look, I'd like to actually make an AMI from this. So I want to create an image. And I could call this my, Ubuntu 1804, test image. I could enable like no reboot, but I actually want the system to reboot. I could add volumes other than the volumes that I already have. Notice this is an 8 gig volume. And then literally what can happen is that in that running system, what it's going to do is it's going to reboot, take a snapshot, and then create an image that I can use as an AMI. I can then make multiple copies of this running system. By the way, I can force it not to reboot. So I can literally take a snapshot of a running system and then just use that as an image. But AMIs are the boot images you use to boot virtual machines. That's what they're used for. You can make your own AMIs. There are tools to make great AMIs. HashiCorp's Packer is probably the most well-known standard tool for actually making automated machine images. It's pretty much the de facto. People usually combine Packer with like Ansible, Chef, or Puppet, or some other DevOps tool to make images. Right? There's Packer.io, by the way. Remember, if I put links in, that's when you want to grab them if you're interested in them. And so, by the way, this can do VirtualBox images. It can do Azure images. It can do images simultaneously. It can do VMware images. So just know, Packer's a great little tool to be aware of. Do note, by the way, that Amazon does have an image builder that has just been released. I'm not really singing its praises just yet because it needs a little bit more maturity before people can use it. But even in 6 months, it won't have the features that Packer has. But it is a great native tool for creating your own AMIs, right? All right, so once you've got a bootable image, you've got an AMI that you're going to boot off of it, you've chosen your operating system, which also, by the way, just to mention this, if I go back to the EC2 console, if I go back into instances and I decide I'm going to launch an instance, what's the first question it asks? It asks me, what do I want my operating system to be? What image am I going to use? Notice that Mac is listed here. Red Hat Enterprise Linux is listed here. Ubuntu is listed here. Windows is listed here. And I just choose my boot image in my architecture because notice I have x86 and I also have ARM over here, right? By the way, you don't really get a choice with the Mac processors. You just have to kind of like deal with your single selection, right? But once you choose your operating system, let's say I choose Ubuntu, then it's going to ask you the next question about family types. By the way, just to mention this before I get into family types, is that, again, you can get pre-built official images from the vendor. Amazon makes your own. You can also just create your own. So Amazon has some. You can get some from the vendors themselves, and you can also make your own images or AMIs, right? Now, AMIs are important because they are repeatable, reusable, and you can use them as backups to recover instances like database systems, for example, as long as the data is also being replicated somewhere, right? If you need to like replicate an installed database or an installed like Tomcat server, for example. So AMIs are very useful. AMIs are stored in kind of a hidden portion of your S3 account, like service. So know that they go into S3. They don't go into any other like location. They're just hidden in S3. I did talk about the image builder just briefly. Amazon does have this new service called the EC2 Image Builder. I will tell you that when Amazon first releases a service, it's actually pretty good, but it's not awesome. It becomes awesome usually after the first year, from my perspective. So in this particular case, I probably wouldn't use the EC2 Image Builder. I would use a tool like Packer for the time being. But the EC2 Image Builder is steadily adding features, so it will soon become awesome. It's going to take a little bit more for it to happen.
I had a question about this, I guess, as it relates to saving out an AMI as you build onto it. What would, I guess, from a process standpoint or a feature standpoint, what would kind of be some of the differences between doing, creating an AMI via image builder, vice, spinning up an AMI, loading what you need onto it, and then snapshotting it out or saving it as a new AMI.
Yeah, so the problem with snapshotting something that you built by hand is that you built it by hand. So if that ever gets corrupted or lost, you won't have a procedure necessarily to do it in the same way automatically and repeatedly. Image Builder will procedurally build your images based on certain steps and code that you have defined. So there's nothing wrong with snapshotting an image that was crafted by hand, but just know that that's not the ideal as far as like being able to create repeatable automated processes for building images. So Image Builder is like Packer, and that will give you a declarative process, not a declarative process, it's actually procedural, but like it'll actually walk through steps to build your image. Snapshotting an image manually is just snapshotting a manual image. And so if you ever need to recreate that image or update the operating system or whatnot, you'll have to go through those steps again.
Would it be safe to say that, like, from a consideration standpoint, snapshotting for backups, Image Builder for creating from scratch?
Image Builder for creating from scratch, but typically your source image is not from scratch. Your security and operations teams will have approved a base image, and then you use Image Builder to build on top of that. So like, for example, they might give you a base Ubuntu image and then decide to give you, well, this is now a new AMI I've built for SQL Server, right? Or Tomcat or Nginx or Apache. So you would use Image Builder to create those customizations. And you might say, well, Michael, why would you want to customize it to the level of the installed application? Because the game, when it comes to EC2 instances, is to get them to boot as fast as possible. Otherwise, they're not useful when you're having a performance outage or like some other kind of degradation. Because if it takes 10 minutes for you to boot a virtual machine, then it's not going to be useful to you when you need it. So
yeah, no, that's perfect, because I'm asking from the standpoint of working through backup and restore processes for a specific application and environment. So we're already doing some work there, but yeah, it's still kind of working towards what the final process is going to look like.
Yeah, the other thing is that if you can build your whole OS to app from a procedural process that's automated and easily executed, then you can easily do it in another region versus another region versus another region. Otherwise, what you need to do is create an AMI of the virtual machine, copy it in, make sure it's a snapshot, and then copy the AMI over to another region, and then pull it up over there. And that's fine. There's nothing wrong with that. Sometimes it's better, though, just to create them independently and distribute them out across all of your regions. So you get efficiency at scale when your process is more procedural.
Okay, and this is skipping ahead a little bit, but along these same lines. So if you've got, from I guess a backup and restore standpoint, and you've got an AMI that you're working from, and you've got separate EBS volumes that are backing that for storage. I guess if from a backup and restore standpoint, would it be easier than just to rebuild the image to the base application that you're talking about, and then reattach the backed up EBS volumes to it and continue on?
Yeah, that's typically the case. Is that when you image a particular like box and it has like say 5 disks on it, it's going to make a snapshot of all 5 of the disks that are on the system. So and then like if you wanted to keep that snapshot and then like restore the whole thing in its entirety, that's fine. But to your point, let's say that you've lost the system and you just want to restore the core box, the operating system, but you've got the data disk, right, for the system in question, then you're right. You can just reattach it, attaching it to the same version of, let's say, database, for example, or Tomcat or whatever. I actually ran into this the other day. Someone got an emergency notice that their system was going to be rebooted, and they ignored it. And then their system was rebooted, but it was an older generation of box, and it was running Postgres, like, I don't even know, 11 dot something. And they had their data disks, but the operating system shut down. Well, by the way, when they were using instant storage for their boot disk, and so they lost their boot volume. which instant storage is an older class of storage inside of AWS that it's recommended that you don't use. But this system was a database and it was years old. So Amazon gave them a year's worth of warning that this was going to happen. They kind of ignored it. The system crashed and they called me and they were like, hey, what do we do? And so we actually procedurally rebuilt an image for them that had Postgres 11 dot whatever 6 or whatever was on there. And then all we did was reattach the data volume. Postgres revalidated the data files, locked them up, and then continued on. We had them up and running in probably like an hour and a half, which from scratch was actually impressive. You know, obviously if that was production outage, we probably that wouldn't meet our standards, but you know, so we did the exact same thing you described, right? We just rebuilt a system with the same version of everything they had, reattached the disk, the database scanned the files, locked them up, and then basically it was like, we're ready to go. Is that helpful? Am I answering your question? I feel like I'm kind of around.
No. Yeah, no, absolutely. No, that's hugely helpful. Yeah, like I said, we're it's something that we're working through, and we've got a lot of other variables going on. So you know, any I guess use cases or examples, or you know, are a huge help.
Okay. Yeah, and so taking disks off, adding disks on is trivial, even if it's the boot disk, by the way. So moving disks around is trivial in AWS. The only catch is, and this is for everybody to really know, is that unless it's an AMI or a snapshot, which a snapshot is just a backup copy of a disk, any disk volumes that you have, they're called EBS volumes inside of Amazon, are local to the availability zone. So you can't take a disk that's in availability zone like US East 1A and move it over to B directly. You have to copy it up as a snapshot and then create a disk off of that snapshot that then lives in B. So just know that once it's snapshotted, it's regionally available, but it's not live. But you can create copies of that data into any of the regions. But when you have a locally attached hard drive, the EBS volumes, they have to be snapshotted before they can move to another availability zone. So just something to keep in mind. The only other argument I would make against Image Builder, by the way, is that this isn't cloud agnostic. So if you are looking at a multi kind of cloud setup, Packer will support all of your use cases. Image Builder is going to be localized to AWS. Now, I love AWS. I think they're a great platform. They are my favorite by far. But you know, the reality is that businesses in some cases need to run workloads in other clouds. So Packer would be your friend there. Okay. Now that's all just about choosing the boot image. That's all that was, right? We haven't even gotten into disk management yet, but that was some kind of disk management conversation. Now, what if you need to customize the system when it boots? Which, by the way, you might be hooking it into a Chef, a Puppet, an Ansible, or some other kind of configuration management system, and this is where you would do it. So underneath user data, what would happen is that when the system boots, you would actually give it instructions about what to pull down, what to install, what to talk to. And by the way, this is, you know, in this particular case, since it's a Linux box, it could be Bash, or if it was Windows, it could be PowerShell. And you just tell it what to do. In this particular case, you're telling it to update all the packages on the system, start the Apache web server, and then turn the Apache web server on so as the system reboots and starts. This happens upon first boot, by the way. Doesn't happen upon second or third boots, never read again. And this is called the instance user data. So this tells the system what to do upon its first provisioned boot. And you can put a long set of instructions in here, whatever you feel comfortable with. In this case, they're putting a set of instructions in here, but there's this special data layer that encapsulates all EC2 instances, and it's called the metadata, the instance metadata. So if instance user data is how you control how the system boots, instance metadata is data that you can retrieve during the boot process with a simple curl, and it actually lists the command right there, where you can pull the host name, pull the IP address, you can pull the IPv6 address, you can pull the security group that's in, right? This allows you to pull data during your scripts so that you can actually get the data that you need while the system is booting. Now, this is awesome. And by the way, this shows up in the exam a lot. So everyone should memorize this 169.254, 169.254/latest/metadata. Forget the public host name, forget the instance ID. You don't need that. But that URL right there, that whole HTTP 169, that is strongly referred to on the exam at least once, sometimes 3 times when you take any of the exams for the most part. And it's either going to be latest dash metadata, or it's going to be / latest dash user data. And metadata will get you information about the box. User data will tell you what someone told the box to do when it first booted, right? Because that's what we're looking at now is user data with some metadata thrown in. So that 169.254, by the way, is a reserved special IP address that kind of like just means like local network stack. And so it's used by Amazon to use local loopback so you can retrieve data off of that particular URL. So that's user data and metadata, which is used to configure the system at boot time. So we talked about AMIs. We talked about configuring the system with user data at boot time or pulling metadata if you need information programmatically about the box off of the URLs I just posted. How do you store data? Well, Elastic Block Store is the virtual hard drive service with AWS. There is also another storage called instant storage that can come with some of your EC2 instances. That is only for temp data, temp tables, temp files. Do not use that to either boot the system as a best practice or to store anything meaningful that you can't lose. It is super fast storage because it's NVMe RAM, NVMe disks, but don't mess with that. That's like, it's just risky. And everyone I know has been bitten by it in some form or fashion. But if you want to be able to reboot a box or rip a disk off and put a disk on something else, then you're going to need EBS because EBS is the hard drive service for virtual machines. EBS only works with EC2. I mean, don't get me wrong, you can mount it with like containers and stuff, but those are also sitting inside virtual machines, right? So, but EBS is the hard drive service. Now, just to say this, typically it was designed to be one-to-one. You got one virtual machine and you've got an EBS volume and other EBS volumes, and they're only attached to one virtual machine. For some reason, Amazon has introduced this concept of multi-attach, which they just did within the last 6 months, that allows you to attach one EBS volume to multiple EC2 instances, but you can't do that unless there's a clustered file system on the disk. So I don't really know what Amazon, where they were headed with that. I'm sure there's like probably like Oracle Rack kind of like systems where they want to attach multiple disks to the same system. That makes sense to me because Rack does have a close, I think it's the OCFS, the cluster Oracle cluster file system. But for the most part, most of us are going to be attaching a disk one-to-one instance, not to multiple instances. But just know that EBS does have a multi-attach function. I actually found it before they announced it because I saw this feature in the API and I was like, what is this? Now, there's 4 types of drives inside of AWS. 2 of them are solid state backed. There's general purpose SSD and there's provisioned IOPS SSD. General purpose is the de facto go-to system when you just don't know what your performance profile is going to look like. And just to be clear, you have to use an SSD to boot. Your boot volume always has to be a solid state drive. Amazon will not let you use a mechanical drive to boot your virtual machines because performance is so much slower. But there's general purpose. The code name for this, by the way, is GP3. And then there's provisioned IOPS, which is now IO2. There were previous versions of GP2 and IO1. Don't use those anymore. There's nothing wrong with them. But the GP3 and the IO2 are faster and cheaper than the previous generation of disks. So if you're using GP2, you probably want to convert to GP3. Most of the time, that's a pretty painless endeavor. If you're using IO1, you probably want to convert to IO2. But IO1 and IO2 are provisioned IOPS versions. GP2 and GP3 are general purpose SSD versions. Now, general purpose SSD can burst, if I remember correctly, up to 16,000, sometimes 32,000 IOPS, depending on the system. That's a lot of IO per second. All of the volumes, every hard drive in EBS maxes out at 16 terabytes. That's the largest volume you can have for an EBS volume, regardless of the family. So provisioned IOPS can go to 16 terabytes. General purpose can go to 16 terabytes. Provisioned by IOPS, by the way, you can turn the dial on that and get to 120,000 IO per second on a provisioned IOPS. Amazon's coming out with a new block express storage. I think it might already be out here in beta. The single volume will do 256,000 IO per second. And it's not 4K chunk sizes, it's 256 kilobyte chunk sizes, which is massive for a disk drive. And I gotta tell you, the performance they're squeezing out of these little iSCSI drives is mind-boggling. So just know that whatever performance characteristics you're looking for, it's probably going to be in the solid state family. They do have a mechanical family. This is the HDD family that is cheaper, colder storage. You can't use these for boot drives. They also cap out at 16 terabytes per volume. But the throughput optimized HDD is a mechanical drive that's really good for like streamed successive workloads, sequential workloads. The cold hard drive is good for nothing but archival storage. So remember, general purpose and provisioned IOPS are the two SSD drives. Throughput optimized and cold HDD, which are, by the way, known as ST1 and SC1 respectively. Those are the mechanical drives. You cannot use these as a boot volume. All drives cap out at 16 terabytes, but their IO footprint is very different. SSD drives can usually go from 16,000 to 128,000 IOPS per second, IO per second. These drives, their IO is really relatively low. They talk about the throughput for these things in terms of megabytes. Now, there are instances that are optimized for their disk drives. And just to say this is less of a concern now, because almost every Amazon instance that you get that is of the current generation, which means either it's 5 or 6, they're all EBS optimized, which means they're optimized to have network disk drives. So you don't really have to worry about this so much anymore. You have to worry about this if you're using older instances, because then it used to be a checkbox that you have to check to make it EBS optimized. So just be aware that you want to use the latest generation of instances as much as possible. And if you've got older instances, you want to convert them, because Amazon favors the newer instances, and the newer instances are cheaper and they're faster than their predecessors. Now, let's say you don't need a direct attach storage and you can't direct attach S3, but you need to be able to share a file system across a couple hundred, if not 1,000 servers. So we're not talking EBS, because that's typically a one-to-one I'm mounting inside of an operating system, but it's not meant to share across hundreds, if not thousands. Don't get me wrong, you can multi-attach an EBS volume, but only to a few systems. EFS, which is a network file share, that is NFS and Microsoft's like SMB CIFS file system available at amazing scale. So EFS is the next kind of file storage, and this can be mounted inside of an operating system. So EFS can handle tons of Linux workloads. So this can be like the NFS protocol 4 and 4.0 and 4.1 are the NFS protocols that this runs. EFS can actually run across an entire region. So if you're in Virginia and you need to share a file system with servers in all 6 of your availability zones, you can create what's called an EFS kind of primary, and then put mount points in each of your 6 availability zones, and they will all be reading from the same file system. This looks like just part of the local file system, but it's actually a network drive being served out by a network server out there on Amazon's ecosystem. Now, FSX is the Windows version of EFS, and it's for Windows workloads. So there's FX for servers, and then oddly enough, there's FSX for Lustre, which is a high performance file system. And if you've dealt with Lustre before, you know what it is. Basically for high performance block computing for HPC and large batch like data processing. Now, these, by the way, will only run in a single availability zone. So EFS will run across an entire region, but FSX will only run in a single availability zone. So Just something to be mindful of. These are high performance local systems. This is high performance regional systems. So for like learning and exam purposes, EFS is for Linux and it's mainly for NFS in the skies, cross availability zone, but not cross region. FSX is for Windows or for Linux file systems running Lustre, and it runs high performance inside of a single AZ. Now, we've been talking about EC2 instances and their like boot images. We've talked about user and metadata, and we've been talking about like their attached hard drives and their network hard drives. But we haven't even really talked about like the sizes of these instances. So Amazon has an interesting format where it's the letter, number, possibly more letters, then a period, and then the t-shirt size of the instance. Let me give you an example. There's a great website, and again, I'm gonna post these websites out, right? So when I put them in there, you want to definitely grab them, right? EC2instances.info. By the way, a company called Vantage just bought them, so it's now called instances.vantage.sh. But what this does is this takes you to a website that allows you to search, because it scrapes Amazon's API. It allows you to search all of Amazon's instance types. Now, I just want to say this. We were just looking on our sheet at the M5. So let's say we type in M5 large. The M5 large, by the way, is an 8 GB of memory, 2 virtual CPU machine that does not have any instant storage. Because remember, I mentioned before that instant storage is not EBS storage. It's like local storage that you will lose if the system crashes or reboots. This has a 10 gigabit connection to the network, and it's going to cost you about 10 cents an hour, which is going to be $2.40 a day, and which is going to end up being about $60, $65 a month, right? That's pretty good, actually. $65 a month for a 2x8 system that's got a 10 gigabit connection to the internet, which, by the way, good luck saturating that. I've tried. And then, of course, you're going to pay a little bit for storage. But I mean, if it's you saw, it's probably going to be like, $20 or something a month, right? But let's say you come back, and so this is the M series. The M series is the general purpose or median series. This is the 5th generation of this series, and its size is a large. If I type in extra large, guess what happens? Everything doubles. Everything doubles, right? So now what's happened is that I now have 16 gigabytes of memory and 4 CPUs. If I put a 2 here, guess what happens? I'm now double an extra large. I've gone to 8 CPUs and 32, right? By the way, I don't even know if a 4 exists. Oh, guess what? A 4 does exist. 64 gigabytes, 16 CPUs, right? So notice that every time I put a number in here, by the way, not all the numbers exist, so don't be fooled. You're like, that guy Forrester's a genius. Just knows the numbers off the top of his head. No, I'm guessing. I could get this wrong, right? By the way, if I take out the t-shirt size and I want to see all the M5s, guess what? Here's all the M5s. I've got the large, the extra large. Ignore the middle for a second. I've got 8, 4, 2, 24, 16, and 12 extra larges here. Notice the hourly cost starts to go up, especially when I get to high instances. It's $5 an hour, basically. Notice the network bandwidth goes up. All of this are EBS backed. By the way, this cost is Linux on demand. So with an unlicensed operating system like Ubuntu or Amazon, you pay per second. With any other operating system, Windows, Red Hat, what's another one? Mac, you're gonna pay per hour. And not only that, with Windows, if we scroll over to the right, notice that the costs here are very different for Windows versus Linux, and that's just the Microsoft tax, right? Microsoft, they have to pay for licenses to run Microsoft, so it's more expensive, right? So notice it's $2.30 over here. It's $4.50 for the Windows version. So by the way, if I start a Linux box and it's Red Hat and I stop at 30 minutes in, I have to pay for the full hour. If it's a Linux box and it's Ubuntu and I start it for 30 seconds and then I kill it, I pay for 30 seconds worth of usage. That's a good question, Sean, because they're not listing pricing, but let's go take a look, see if we can find it. So here are the Mac instances. Pricing, here we go. So for example, in North America, is per second. Oh, so Mac is also per second. That sounds good. With a 24 minimum allocation period. Ah, okay. So you have to pay for the first 24 hours. So when you start a Mac, you have to pay for the first 24 hours. That's crazy, by the way. That's intense. I did not even know that. Oh, wow. That's crazy. I'm sorry. I'm totally shocked. I did not know that, Sean. That's a great question. Notice that here the price per hour is $1.83 for the Mac systems. I don't know if that's because there's some kind of limitation on them, but I actually haven't run any Mac instances thus far because, quite frankly, I just don't see the need for that. Mac is not interested in playing in the enterprise space, so I haven't felt any need to change that to mess with Mac instances. I just stick with Linux. But man, that's a thank you for that, because that really taught me something. I'm gonna have to go back and look at this now, because I didn't realize there was a 24-hour minimum commitment in order to start a Mac instance. So if you start one for an hour, you've paid for 24. Woo, that's interesting. So by the way, if you're in the EC2 and you decide to launch an instance, one of the questions it will ask you is like which of these you want. So, but that does beg the question, Sean, just to say this, if we go to the simple monthly calculator for AWS and we change the operating system to Mac, let's just try this for a second. Oh, they don't even have Mac on here. That's how old this is. We have to go to calculator.aws. We'd have to create an estimate here. I wonder if they have Mac actually on the estimations. Let's see. So I see Linux here. I don't see Mac. So there's no cost estimation tool right now for Mac from either of the two official like websites, either the simple monthly calculator or for the calculator.aws. That's a good. So yeah, that's a good deal, Sean. Just to check, do you have a use case that you need Mac for, or is it just like for like testing and vulnerability purposes?
No, I was just curious because I had heard here recently that they had done it, kind of forgot about it, and then you mentioned it again, and yeah. So yeah, when I was looking at the specs that you were throwing out for the for the different examples, I just figured I'd ask.
Yeah, no, thank you for asking. That was kind of a little bit of a shocker. So thank you for giving voice to that. Wow. So as far as like the t-shirt sizes go, right? One thing to note is that there are actually a lot more letters after the number, because Amazon just recently either diversified from Intel only processors to ARM, which is also Intel, to AMD, but also to their own processors called Gravitron they just designed. And so if we look at this, for example, the M6 series, this is a Gravitron processor, which is part of their kind of Nitro series of systems. So just know that in addition to the t-shirt sizes, in addition to the first letter, which is the family type, in addition to the number, which is the generation, there's also additional letters that will give you the instance types. Now, none of these letters show up on the exam except for the family type, which is the first letter, the generation, and then your t-shirt sizes. That's it. And they don't expect you to memorize the t-shirt sizes. They just want you to know that you need to use the latest generation. So your number needs to be as high as possible. And they want you to know what the M, the C, the R, the P, the F series, the H, they want you to know what those series are, right? So just be aware that M stands for median or average. The R series, of which there is an R6, is the RAM series. By the way, what this means is that means the ratio, let's just choose actually an RG large. The ratio of CPU to memory is 1 to 8. If it's the M series, the ratio of CPU to memory is 1 to 4. And if it's the C series, which I'll show you the C series here. The C series, notice it's 1 to 2. So the C, the M, and the R's are increasing ratios of CPU to memory. So the C series is a 1 to 2 from CPU to memory. The M series is a 1 to 4 for CPU to memory. The R series is a 1 to 8 for CPU to memory. So you want to make sure that you know what those ratios are, because quite frankly, the other things don't really matter. Like honestly, 10 gigabits of backplane bandwidth is super fast, and the slowest system on here is 5 gigabits. The fastest one is 100 gigabits. Most of us are not going to saturate that level of backplane. EBS is independently configured, so you don't have to worry about disk characteristics. By the way, if you come in here and you say, you know what, Michael, I want to run an idea, but I don't want to pay like top dollar. The T3 series, by the way, of systems, and this, by the way, includes the T3 large, which is a 2x8, or the T2X large, which is an 8x32. These are, I call them the test series. Amazon doesn't call them that. They think they're general purpose. But these systems will not run at 100% for 24 hours. Notice there's a burst credit listing here. These systems are really for test systems, or you can run them in production if you know what you're doing. But the T series is considered general purpose, like, and also for testing. The M series is considered for general purpose, but and you can use those for testing, but you don't need to. The R series is the RAM series, so that's memory. The C series is the compute series, so that's mainly focused on compute. There's other instance types out here. For example, there is the H series, like the H1, which is used for data. There is the I series, I3, which is used for I/O. These guys are super fast, but they've got some specific design things that you need to be aware of. There's the D3. I don't think there's a D4. There's the 3 series, which this is for data warehousing. So the D series is for data warehousing. The I series is for high I/O. The H series is for general disk optimized, like database like systems. There's also, by the way, the P series, which has GPUs attached to them. There is the G series. Oh God, what is the latest number for the G? I forgot. Let's take a guess here. G3? Nope, G4. So the G4 series, by the way, actually has NVIDIA network cards attached to it. Right? So these are pretty robust systems that have like up to 16 network cards attached to them, depending on which system you're talking about. So the G series is very much focused on GPU. So you got to remember the G, GPU, C for compute, R for RAM, M for median, T for test. Amazon, by the way, thinks T is for general purpose, but that's not what it's really used for. There's the I series for I/O, D for data warehousing. So there's a bunch of like, you got to memorize at least the broad strokes around the family types. And so like in this particular example, this now makes sense, right? Because the T2 large is a test series. The C5 extra large is a compute series, and the P series, well, that's a little weird, but it's more of like a video card series, right? The P's and the G's, and I think the F is another one. Those are all like video card series. So here's the sizes, and I already pointed out that they double as they scale. Here's the different like types, so make sure you use the right type for what you like. If you need a 1x2 system or some variation, then use the compute system. If you need a high memory system, then use the R series. If you just want an even spread, then use the M series. So here's the family types. I'm actually going to stop here and leave this up so that you can look at it if you want to. But we're actually at 12 o'clock, and I promised that we would stop so our brains could like catch up with all this information that we've been taking in, right? So I'm going to leave this up for in general, but we're going to take a 60-minute lunch. We're going to come back at 1 o'clock. It's 12:01 right now. Before we stop, does anyone have any questions they want to give voice to? Okay. All right, let's come back in 58 minutes. I'll actually put up a tiny little timer also in the upper left-hand corner so you can kind of know, but we're going to come back at 1 o'clock. That's when we're going to start again, okay? Otherwise, I will catch you. Step away from your computer, get some water, eat food, go hang out with friends, take a walk, do whatever. Otherwise, I'll see you in 58 minutes and we will reconvene at 1 o'clock, okay? Thanks, everyone. Any questions about EC2? No? Okay. Now that we've been staring at this slide for an hour, a little quiz for you. Okay. So you can ignore this one. What is the family letter for the general purpose instances? Not the test instances, but the general purpose instances inside of AWS. What's the first letter? M, that's right, M for median, right? So M is the general purpose family, right? I already talked about TATs, the test, right? There, by the way, Amazon classifies that as general purpose also, but they're really test instances. All right. By the way, in this chart actually talks about why they're not really general purpose, because just so you know, when you get a T series, the processors are capped out at that baseline performance. And if you want to go beyond that performance, you have to spend credit hours. Now, credits accumulate for every hour that the system is underneath those baselines, like it's basically not utilized. So understand that when you get a T3 2x large, it can burst up to 100%, but it can only do so for as many credit hours as it has available to it. Right. So as you can imagine, you can run at 40% consistently, but if you run above 40%, you might burn through your credit hours, right? So that's why the T series, in my opinion, is a test series, because until you really know what your workload is and what you're doing, you can't really use these series in production. Okay, all of the exposition around the T series aside, what is the family letter for the high memory systems that you would use where the ratio of CPU to memory is 1 to 8?
R.
R. Yep, good. Good. Multiple guesses there. The RAM series, right? All right, what's the one for the compute? That was pretty straightforward after we did the other two, right? C, that's right, the C series. Okay, now this one's kind of a stretch. Give me any of the family letters for the GPU accelerated computing series. Any of those.
PGF.
Good, good, PGF, exactly. Yeah. All right, and now give me any one for the data series, other than D.
H.
H. H is probably the most modern of the series. The I and the D series, like the D3 and the I4, is that the I3? They haven't been updated in a while, actually. So the H series is really the kind of latest generation, if you will. Note again that if there are letters after the number, that's a special appellation. So let's take a look at that for just a second, because I want to make sure that we're clear on that. So EC2 instance types. So if we go look on Amazon's webpage, you'll see, for example, that there's not just T4s out there, there's T4Gs. I already told you that the G stood for Gravitron, which is basically a special processor that they built, the Graviton 2 processor. And it's ARM-based, and it delivers 40% better performance if your binaries can handle ARM, right? Which most of them can, but if they've been compiled for something else, they're not going to work on ARM, right? But like, for example, here's the ZN series. What's the ZN series, right? Well, this is obviously using Xeon processors, which I'm assuming that's what the Z stands for. It also has, I believe, NVMe storage on it, which I think is what the N stands. Oh, Nitro. It's the Nitro system, which means that it's a faster integrated system. It's a hyper-converged system that you're getting a virtual machine for, and it's super fast, both from an I/O perspective and a memory perspective. A typically stands for AMD. Sometimes it stands for ARM, which kind of throws you off. Like here are the T3As, right? These are using AMD processors as well. There's actually a D series somewhere here. Let me scroll down a little bit. There's the A's and N's. N is for Nitro, A is for AMD. There's the A's. Oh, there's the B series. These are EBS optimized variants of R5s, but just to say this, the R6s are automatically EBS optimized, right? So it's like, The N series, by the way, has NVMe RAM on it. So this is, I'm sorry, hard drives. So they're like super fast hard drives that are attached to it. Anyway, you get to learn all the little subletters. They don't test you on the subletters. They don't test you on the A's, the D's, the G's, or whatnot. They do want you to know that G is gravitron, right? But for the most part, they don't test you on the letters. They only grab you on the first letter and the number. That's it. And really, they're not testing you on the number. They just want you to use the latest generation of the number. One thing I was going to say is the A1 is an ARM-based workload. That's the ARM systems. Yeah. So, all right, good. So that's the general thing to remember here is that those are the family letters. Always try to use the latest generation. Know that sometimes you'll switch from Intel x86 instructions to ARM instructions if you go to the latest generation, especially if it has a G after it. So just something to pay attention to. They typically will maintain an Intel-based and an ARM-based, like current version of systems as things progress. So they're pretty good about making sure there's still backward compatibility. All right, so I already talked about the T. C, we've kind of talked about already. You should kind of feel about like these are the compute instances. There's nothing special here other than this is a 1-to-2 ratio of memory to CPU, right? Notice here the R5 series, 1-to-8 relationship between CPU and memory, right? Notice, look at those networking speeds. 10 gigabits, 25 gigabits for a 24 extra large. Just so you're aware, that is not network card dependent. There's always at least one, most of the time, 2 network cards on these systems. If you add a third, a fourth, and a fifth network card, which you can do easily, it doesn't actually change the available bandwidth. That's just a management partition. That's all a network card is in the EC2 landscape. Adding more network cards does not increase your throughput on your boxes. That, by the way, shows up on the exams. I think I actually last saw that on one of the professional exams. But just know that it doesn't change your bandwidth. Here's the accelerated, the P series, right? The P3s in particular. Notice that this has a P2P link for GPUs called NVLink. Look at the size of some of these boxes. Amazon, by the way, does have bare metal boxes. You can actually get a host that you can install your own hypervisor on. I have no idea the prices. No one I know has ever gotten one. These are 448 core boxes with 24 terabytes of RAM. I have no idea what they cost. I suspect they're expensive, more expensive, right, than the traditional virtual machine. Here's the H series storage optimized. Note that this has instant storage attached to it. Word of caution, that is the 5th type of storage other than 2 SSD backed and 2 mechanical backed systems. If you use instant storage, just know if that system crashes, all of the data on that instant storage is gone and you nor AWS can recover. So only use instant storage drives, either not at all, or for temporary data that you don't mind losing because you can recover it easily. I want you to know that I'm about to skip through all of the Intel Xeon CPU slides. Why? Because this is in here because of, I think, a contractual obligation with AWS. This just says that there's a bunch of really advanced features with Xeon processors, if you want them, by the way. Like if you need enhanced encryption acceleration or whatnot, then there are instances that will give you access to the processor, right? Amazon does use the latest generation of processor with those types. They also, by the way, provide their own processors and AMD processors. I wouldn't be surprised if they started offering Apple's M1 processor soon as well, depending on how Apple's going to license that M1, right? But just know that you can get access to like P state and C state control and stuff like that inside of Amazon if you really want it. These are the instances that give you access, that can give you access to those advanced features inside the processor. Notice that it's not really the latest generation. Don't get me wrong, the R5 is the latest Intel generation, but the R6G is the latest ARM generation. T3s obviously are the latest generation for the Intel-based systems, but a T4G is the latest actual generation of the T series. Just a reminder, I've said this several times. if you have a choice between a 4, a 5, and a 6, assuming it meets your other needs, go for a 6. Don't use the 4. Because you're actually going to get better performance per dollar off the latest generation than you are off of prior generations, right? And every time Amazon does that, they give you more power at a lower price, and they continue to do that. They've probably done that like 7 or 8 times per instance family. Sometimes they just lower prices. Sometimes they give you a new generation of instances that are lower price and they are more performant. So just be aware, they do that a lot. Okay, that was a lot on all the different flavors and variations of EC2 instances. Any questions? Okay. When we do our short review tomorrow morning, I'll ask you again about the different family sizes and types. Okay. Let's talk about all the different flavors of licensing that you can get with particularly EC2. But I want you to be aware that there are, for example, reservations or reserved instances. They also call them reservations, by the way. You can get reservations for DynamoDB, for RDS, for all kinds of other services. So just because we're talking about EC2, just know that there are reserved plans for other services. There's also savings plans for other compute types like Lambda and containers. I just want you to be aware, everything has an on-demand version. Not everything has a spot version. Matter of fact, EC2 is the only one that has a spot version with it, okay? So, but I want you to know that those saving plans and reservations, those actually can apply to other services. There's a great white paper about how pricing works inside of AWS. I will make sure you have a link to that before we leave on Friday. Totally worth reading, because remember, every design decision, every checkbox inside of AWS either has a security or a cost implication typically. So I want you to be aware of other types outside of EC2, but just know we're going to focus on EC2 for the next little bit. Okay, so on demand is the way that most people use AWS. You put down a credit card behind your account and you pay almost full retail price for that instance because you have no contract and no relationship with AWS other than your credit card. You also, by the way, it means there's the least amount of restrictions. Because you are paying full retail price, you can give that instance back at any time. You owe Amazon nothing. There's no obligation on your part, except for like the exceptions, like we were looking at macOS earlier, right? Except for those exceptions, there's, other than those little rules, there's no obligation. So you pay what the rules say you pay per hour, pay per second, you're done. No upfront payments, and you just add or increase capacity depending on what you need. Now, that doesn't guarantee, by the way, that if you ask for 1,000 instances, that you're going to get 1,000 instances. 10, probably. But when you do on demand, by the way, just be upfront about it. You are the least priority in the totem pole when it comes to when people request instances. If there are people who have a relationship or a reservation with Amazon, they're going to get their instances before you do. Now, I don't want to create fear, uncertainty, and doubt, because quite frankly, I've never not gotten the instances that I needed. I think maybe twice I got a message that said, hey, can you start these instances up in a different availability zone? Because there's no, currently we're out of capacity in these zones. That's only ever happened in Virginia, by the way. It's never happened in another one. There's nothing wrong with Virginia. It's just that most people use Virginia, right? So on demand is full retail price. And we were on ec2instances.info earlier. When we were looking at this, this is on demand cost. See this on demand? That's the highest price compared to a reservation. See the difference here? If you get a reservation with AWS, which means you commit to pay for a year or 3 years, notice the discount here. This is $1.30 difference compared to the on-demand cost. So, you know, that looks like to be what, a 33, maybe 40% savings. That's for 1 year, no upfront. See this little thing up here where it says reservation? Notice how it says 1 year or 3 year? 1 year or 3 year? Ignore this convertible thing for the time being. 1 year or 3 years. So you either pay no upfront, partial upfront, or full upfront for a year, or you do it for 3 years, and that's a reservation. So that's actually the second type. That's not on demand. That is this type, which is reserved instances. Those are also called reservations. You prepay for capacity, and in exchange, you commit to pay for that resource for a year or 3 years. Now, how much do you pay up front? Well, that depends on you. You either pay nothing up front and you don't get as much of a discount, but you still get a discount. You pay like a little bit up front and you get a deeper discount, or you pay a lot up front and you get a fuller discount. I'd be saying, well, Michael, I hear what you're saying, but that doesn't really make any sense, right? Well, let's go take a look. So here we are in the reserved instances section of Amazon. If I want to purchase a reservation, notice that I have to pick my operating system. Let's say I'm just going to go with standard Linux. Like, what does it matter? You have to pick your tenancy because there is dedicated tenancy, meaning nobody else is on that hardware, but there's default tenancy. You can say, look, I just want a standard RI, and I really like the T3 Micro, and I want to get it for 36 months, and I want to do all upfront, right? And so you can search and say, look, if you pay $53 upfront, I will lower your cost to 0.006 per hour. By the way, you might say, well, but Michael, that's a T3 Micro. How much does the T3 Micro like normally cost? Let's go take a look. Let's go take a look, see what a T3 Micro typically costs. Well, typically on demand, it's 0.010 cents an hour. So it's basically, right, 1/100th. It's a penny. It's a penny and some, like a tiny little change an hour. But if I'm in here and I'm like, you know what? If I go ahead and pay $53 right now, I'm not going to pay 10 cents. I'm sorry, 0.01. I'm going to pay actually 30% less. I'm going to pay 0.006. So if I put $53 down, my hourly charge is going to drop. And by the way, usually in about 18 months, you are basically saving money over the on-demand price if you go for 3 years. So reservations require you to run a particular instance type in a certain tenancy, right, in a certain operating system, and you're buying that. And so if you run any boxes that match those 3 criteria, that reservation applies, and that basically drops to 0.006 as far as the discount. Now, if I decide that I'm going to pay partial upfront, and I do a quick search, well, that drops from $53 for a 12-month term to $27. So it's half. And notice that my discount, right? Did it really change? Let's go back to all upfront, take a look. Notice this 0.06. I don't know why the hourly rate isn't like populating, but notice it didn't really change all that much. It just means the term is different. If I go to no upfront, by the way, for that same thing, notice that my rates go up a little. I don't get as much of the discount. I got 0.007 instead of 0.006. So, I mean, this is a cheap system already, right? If I go to a 2.3x large, and if I go to all up front, this would require me to pay $17,000 up front, and then my rate would drop to 0.19. But if I did nothing up front, I'm paying nothing up front, and notice that my rate is still a little cheaper. But like, I don't even know what the normal rate is for a T3 2x large. So I come over here, type in T3 2x large, and normally it's 33 cents. Holy cow. That is a huge difference. It's 33 cents, but over here with no upfront, if I put nothing down and I agree to pay that for a year. Oh, actually, sorry, this is 3 years. Then what happens is I get, a huge discount. So just remember, you have to pay either for a year or for 3 years to on that resource. And by the way, if you have no box that matches that profile, you're still paying for it. That's a getcha, right? When you buy a reservation, you pay for that box even if you're not using it. You can, by the way, sell reservations in what's called the reservation marketplace. So there is a reservation marketplace. Oh, where is it? God, I haven't seen this thing in forever. Where is the marketplace reservation? Oh, I haven't seen this thing in like years. I don't even know where it's at now. But there's a marketplace that basically allows you to sell your reservations out on AWS. You usually get pennies on the dollar. Not pennies on the dollar. You get like 10 cents on the dollar, basically. But you can get pretty close to full price if someone's desperate for your reservations. But you can sell them. Oh, here it is. It's actually in here. If you have a reservation, you just click on sell. They moved it around from where it was a couple of years ago. Okay. So that's reserved instances. So you've got on-demand instances, which is just full retail price. You've got reserved instances where you pay a 1 or 3 year commitment. And you can, by the way, get standard RIs, which are very fixed, or convertible RIs, which are a little bit more flexible. You can also get RIs for a certain period of time. So standard RIs are 24/7, meaning you pay for a box that runs 24/7. Scheduled RIs are you're saying, look, I only want to pay for a box, for example, if it's available from 8 a.m. to 8 p.m. Monday through Friday. So scheduled RIs are very much like standard RIs, but they're a subset of 24 hours. And your discount isn't as cheap as a result. If you have an AWS organization that has multiple accounts inside of it, and you buy a reservation anywhere in the account, it applies to any box, any EC2 instance that's inside the account. So do note that reservations will go cross account if the accounts are linked. So that's important to know.
I got a question about the the standard RI. So if you've got a system that has there's some sort of failure and you need to restore or spin up new instances, and it's normally a 24/7 365 system, how does that impact pricing when you have to terminate old instances, spin up new replacement instances, but again, it's still a 24/7 requirement?
Well, so for example, let's say you buy 5 reservations of a certain type of box, and you've got 10 of the boxes. And what happens is it's like a ticketing system. It's first come, first serve. If a box starts that matches the reservation's characteristics, that reservation is associated with that box. If that box is deleted or fails or crashes or for whatever reason, and there's another box that has the same matching criteria, the reservation moves over to that box. So your reservations will always attach themselves to any box that you have that matches the reservation's criteria. So you never have to worry about your reservations not actually working, because as long as you have one box that matches that reservation's criteria, the reservation will move to whatever box matches the criteria at the time. So you will always get your discount.
Okay, nice. Okay, thank you.
Yeah, because it's like a ticketing system. It doesn't attach itself to a box like persistently. If that box goes away, it just moves over to the next box. So, and those reservation kind of like tickets are just hang out there, and they figure out where they should be attached, and your bill reflects it as well. So your bill will tell you, it'll say, hey, these instances all were attached to reservations. And just so you know, this kind of freaks people out, is that when you look at your bill, if you have reservations, you pay for all of them on the first day of the month. So sometimes when people are doing forecasting, if they just bought reservations, let's say they spent $100,000 and just bought reservations. What happens is that at the first of the month, you pay $100,000. And so what happens is that when people are like, wait, but my bill is usually like $5,000 a day. What just happened, right? And so they're used to like paying like 30 days, like like $150,000. But on day one, they're paying $100,000. Just know that when you attach reservations to your account, you pay for them in their entirety. For the entire month, you paid for them on the first of the month. So your first daily bill is going to include the entire month's worth of reservations. So it can really throw you off if you ever have to look at somebody's bill. You're like, oh my God, we're already on track for $100,000. It's like, no. You paid for the entire reservation set for the month on that first day. So just FYI. Other questions? Okay. Now, savings plans are interesting because you can buy compute hours in a savings plan. You like prepay, like you buy like 100 compute hours. And every time you run an EC2 instance or a container or serverless, it eats away at your bucket of, compute hours. Now, in exchange, you get a discount for prepaying and buying compute hours. You can get up to 2/3 off, right? And so savings plans, when you buy these buckets of compute hours, they're not really compute hours. They're called, like CMUs or something. Basically, what happens is that you buy them for a region and an instance family. You say, look, any M series I run in US East 1, I have 100 like compute hours for it. And if you start an M5 2x large and M7 4x large, it eats out of that bucket. And then when the bucket hits 0, then you start paying on demand price. Otherwise, you pay the discount price for your compute. Now, compute plans are weird because if you go inside and you look at like EC2, they actually just added it in so that you can actually purchase a savings plan inside your account. And so what happens is like you can say, look, I'd like to purchase a savings plan. And you have compute savings plans, which can apply to any compute usage. You have just EC2 instance plans where you're like, it's only for EC2 compute. And Catherine, I think this is probably more for you, although maybe you don't have to deal with this, and I hope you don't, actually. You can actually get SageMaker savings plans if you want to actually like save on SageMaker compute, right? So just know that savings plans, if you can like, it basically you buy a consistent like level of compute every month, and it's for like a 1 or 3 year term, very similar to reservations. And it's measured in like, I want to say it's like either dollars per hour. Sometimes it's like compute dollars per hour or some like variable. Your commitment, by the way, you put in the dollar amount. You specify whether you want to do a full upfront, like you want to put in like a balloon payment or no balloon payment, and then set the start date and then just go to town. So remember, you will pay for this. You do need to use it, right? So make sure that you're not over purchasing like, oh, I might use it. Make sure you've got a plan to use it. So that's savings plans. So savings plans are interesting because it's like you buy a bunch of hours and you just kind of sip out of it, right? And then last but not least is spot instances. And spot instances, I used to say that these were the eBay of, but I don't know if you noticed, but this took me to my cost management interface. I'm no longer in EC2. That's why I used to say that's a new link. You used to have to go into cost management to find savings plans. Here, obviously, they've now moved it into EC2, so there's a link for savings plans right here. But spot requests, spot is interesting because spot is you bidding on Amazon's extra capacity. So if we go look at pricing history, for example, for a C5 extra large, the on-demand price for a C5 extra large is 0.085. Look at this spot price. Like, take a moment to take this in. That's like an 80 or 90% discount off the on-demand price. And this is US East 2A, 2B, and 2C. Look at these spot prices. This is like 80% off. But there's a hidden cost here. Spot instances will stay active in your account until somebody outbids you. So if someone comes in and says, you know what, Amazon, I'm willing to pay 0.0192 for this instance, and you put in a spot price of 0.0191, Amazon will give you a 2-minute warning, give you a notice, shut your system down, and then give it to that other account, right? Be aware that this used to be so much harder, but this is only for applications that are writing data out like frequently, like every 30 seconds to a minute, and that can stand to be shut down and they can pick up and continue their state or process from an external data source like S3 or DynamoDB or some other database. Now that I don't want to make that sound as hard. It's not as hard as you think it is. This is great for batch processing. This is great for like genomic data, any machine learning, number crunching, batch processing. This is actually good because it's literally 1/7 of the cost of standard EC2. But you wouldn't use this if you had a deadline. Like, we got 48 hours to turn this around. No, go buy an on-demand instance. But if you had a month to process a report that takes 2 days to run, and you didn't want to pay full price, and you wanted to like be efficient with your costing, This falls right under cost optimizations, right? Because then you can use the spot instance to say, Amazon, you know what? I will pay you 0.02 cents for your C5 larges that are in, whatever availability zones, right? And Amazon will give it to you until somebody outbids you, and then they'll win the bid, right? So just know that you absolutely must understand spot instances and how they function before you can use spot instance pricing. But you've got to be aware of this because this is a tremendous cost savings opportunity. And by the way, I have a workshop on spot instances that I'm going to share with you at the end of the class. Make sure you have access to it. It's free. It's going to require your personal account. I see it's free. Hold on. It's going to cost you a couple bucks, right? To run the whole thing in its entirety, but no more than $2, right? But I've got an unlisted Amazon workshop that covers spot instances and gives you a feel for how to run spot instances in your account. But these are tremendous money savers if you can handle the slightly increased complexity they represent. Now I say that like you bid, prices are now based on long-term trends of supply and demand. So they've kind of like gotten away. That's why I said I used to say it's the eBay. What they actually are doing now is they say, look, this is the price that we're offering it at, take it or leave it. But I mean, isn't that ridiculous? That's like an 80% discount. It's huge, right? So there's no more bidding wars, right? But if someone starts purchasing a lot of C5X larges in this case, and the price starts going up, Amazon will take it away from you. So 2 minutes and that's it, right? 77% savings. It's crazy. Okay. There is, by the way, a fifth option, because you notice that when we were here, they didn't list this fifth option, but there is a dedicated option. So there's a dedicated option if you want to have your own isolated instances or your own isolated hosts. When I was referring to bare metal earlier, that's a little different because you have full control. But if you buy a dedicated host or buy a dedicated instance, you are on isolated hardware. There is no other tenant, no other customer of Amazon on that hardware. Now, I'm kind of curious as how they're getting away with that with dedicated instances, because if you imagine you buy a 2x16 box, how are they isolating that box so that nobody else is on there with you? I literally think they have 2x16 boxes just sitting around that when you buy a dedicated instance, they just put your virtual machine on that hardware. Now, a host makes sense to me. That's when you want to run virtual machines where nobody's on there but you, right? A host, buying a host, that makes total sense to me. But instances like are very fascinating to me. So anyway, these are options for security or licensing reasons. If you're like, I can't be with other customers, this is a great option. This is the most expensive way to use AWS is dedicated instances, dedicated hosts. So just be aware of that. It's also the most secure. So notice that in here with dedicated instances, the instance is physically isolated. Here with a dedicated host, you own the host. Nobody else is getting on that box but you, right? So good. Now remember, if you do decide to do dedicated hosts, you actually have to have a VPC that has dedicated tenancy. So just remember that you're going to have to create a new VPC that's dedicated just for dedicated hosts or dedicated instances. So just something to be aware of. Amazon also has the compute optimizer in here. So if you are, things keep moving around in the console. Amazon like pushes things out to other services. Compute optimizer will basically go in and analyze your resources utilization. You do have to create a service link role, right, for that. And when you opt in, what happens is it will start analyzing. It takes about half a day for it to actually pull this off accurately, but it's going to start analyzing all of your EC2 instances, and it'll look at your Lambda functions, your EBS volumes, and it'll basically say, look, this system's underutilized, you should convert it to this. This Lambda function is oversized, you should convert it down to this. This EBS volume is barely utilized, you should move off of provisioned IOPS and move to general purpose storage. So the compute optimizer will actually analyze your usage and give you reports about ideal optimizations. The longer you can run the optimizer over time, the better the recommendations it will make. So don't just run this for 24 hours and walk away. Run it for at least a week, maybe a month, and then see what recommendations it recommends. Questions on any of that? It is Amazon's best practice, by the way, that you tag, because this will allow you to search, manage, and filter, right, against your AWS resources. Please have an enterprise tagging strategy. Most of the time, this is already dictated to you already, which is awesome. But even within your project, you can actually create your own little micro tagging strategy to make sure that you can find instances, understand what they're used for, not just the enterprise's needs, but what are your project's needs, right? Do you know the role of a particular folder or what applications are on there or whatnot? So tag your instances. It's really important. Tagging best practices is pretty much just do lowercase for everything. Use like colons and dashes to separate categorizations and words. Try to, when you do automated tools, make sure they're auto tagging. Like, hey, this was made by Terraform, whatever. Far better to use a lot of tags than too few tags, and it's really easy to change tags. So don't worry about over tagging or mistagging. Tag like crazy. It's going to help you. Okay, other considerations for EC2. Well, one, just know that if you ever need to closely and tightly place a bunch of EC2 instances together because you're doing high performance computing or there's some kind of like data replication happening, you can use what's called cluster placement groups, right, to place systems together. This will give you HPC level localization, but it will cost you redundancy because many times these systems don't span availability zones. Another thing is that you can do spread placement groups, which says these instances cannot co-locate because they are so mission critical. I cannot have them on the same physical hardware and I cannot have them in the same zones, right? So spread placements groups are used when you want to make sure that components don't run on the same backend physical hosts. And there's a third where it's a partition placement group. So whereas clusters bring you together, spreads push you apart. Clusters put multiple boxes together, but then spreads them apart. So for example, Cassandra does this, it's a data store. Cassandra will allow you to create clusters in each availability zone, but those clusters can't like live in the same AZ. So they're pushed apart, but there's actually a cluster of boxes. So you can have multiple clusters of boxes that locally cluster together and they replicate, like in a sense, globally with their remote clusters. So they're part of a meta cluster and there's like clusters inside the meta cluster. So partition placement groups allow you to say, look, I want these 5 boxes over here. I want these 5 boxes over here, and these 5 can stay in the center, like stay away from each other, right? But I want all 5 of you to stay together, right? So that's cluster, which brings everything closer, spread, which spreads everything apart, and then partition placement groups, which does a combination of keeping everything close, but spreads clusters apart. Oh, it says Cassandra right there. I'm not even reading the slides. So, yeah, good. I'm glad it says that. Whew. Was that a lot of information? It felt like a lot of information. We just went through family types. We just went through licensing types. We just talked about HPC and cluster considerations from like a placement kind of opportunity. Everyone ready? Any questions before we do a little knowledge check? All right. What is an AMI? Which of these answers is correct? You can either say it or type it in chat. What is an AMI? Is it an object that stores data? Is it a block level storage that will disappear on shutdown? Is it used to create new EC2 instances, or is it a type of storage bucket? Which is it? 3. Good. Yeah, it's just a bootable image. That's all it is. It's where your operating system and any kind of other configuration around drives and whatnot are stored. Knowledge check number 5. If you want to choose the host on which an instance would run, which option should you use? Do you use the default, which is shared tenancy? Do you use dedicated instance, or do you do dedicated host? You want to choose where your virtual machine runs. Don't worry, there's no failure here. Swing for the fences. Make a guess. Good. Dedicated host. That's exactly right. Dedicated instance doesn't let you choose where your instance will run, but it will isolate that instance from other instances. Good. Excellent. Okay, so what is EBS? Is it an object storage solution? Is it a block storage device that can connect to multiple instances at the same time? Is it a file storage system that can connect to multiple instances at the same time? Or is it a block storage device that connects to one instance at a time and it can be backed up to S3? Oh, Amazon. This question probably needs an update, doesn't it? Give me the two answers, because there's two right answers here, not one. There's two. Good. Say that again.
3 and 4.
So it's definitely a block storage device that can connect to one instance at a time. But just so you're forewarned, about 6 months ago, they released a version of EBS to everybody called multi-attach, which now allows you to attach the EBS volumes to multiple instances at the same time, as long as there is a cluster file system on the EBS volume. If there isn't, that's going to be a disaster. So the right answer actually is 2 and 4, but Amazon hasn't updated the slide since they released that 6 months ago. By the way, you should still think of EBS volumes as being 1-to-1, even though I just told you that number 2 is also a technically correct answer. Most of us are not going to multi-attach our hard drives. You imagine taking a USB drive and plugging it into 2 systems at the same time? No. First of all, most USB drives don't even have that capability, but you can't, right? Without the right file system on the USB drive. Okay, awesome. That was the end of our compute module. Hold on just 1 second. Sorry, just checking our agenda really quick. Oh yeah, we're doing database layers. Huh, I kind of like pre-warmed those on accident. All right, let's talk about database. By the way, in case I didn't say this, is it Udit? Am I saying that properly? Or Udit?
Yeah, it's Udit. Yeah.
Udit. Okay. So just so you know, you probably didn't see this from earlier, but this is our general agenda today. This is like the instructor's view of our agenda. We're going to be doing basically 2 or 3 labs today. We may not get to the 3rd lab. It just depends on our pacing. Typically, days 2 and 3 are faster. Like we're a little bit faster just because we're more familiar with the process. But this is what we're covering today. We're going to cover the database layer. We're going to do a lab. We're going to do a networking layer. We're going to do a lab. So it's going to be our day. So I am recording, by the way. So just in case I didn't say this earlier, I will obviously share everything with you.
Okay. Yeah. Thank you.
Yeah. Okay. Let's talk about databases. Anyone have any questions about compute? Does anyone know of anything that we didn't talk about? Anyone note that there was something there were a couple things I didn't talk about, right? From a compute perspective. What were the other 2 types of application hosting that I didn't really talk about, other than virtual machines?
Containers and Lambda serverless.
Perfect, Sean, that's dead on, right? Yeah, we didn't talk about containers or serverless. We will definitely talk about serverless. I didn't really see any container stuff in the architecture class, but I know it sounds like, well, Michael's really promising a lot. I'm going to also give you a URL for the ECS and the EKS services that if you do the free, it's going to cost you like your personal account. It'll cost you like $2 to do both workshops. If you do these workshops, you will know more about ECS and EKS than most people I work with. So I'm going to make sure that by the time we leave, you have 3 URLs, one for EC2, one for ECS, and one for EKS. ECS and EKS are the container services, and they don't really get covered in architecture, but containerization is just taking the world over. And I fought it tooth and nail because I'm like, been around forever. I'm like, do we really need containers? No, we really need containers. There needs to be more containers in our lives. No pun intended. So I'm going to make sure that you have those URLs so that you can do those labs and workshops independently. So one for EC2, including Spot, which I just talked about, one for ECS, the Elastic Container Service, and another for EKS, the Elastic Kubernetes Service. And these are AWS official, public, unlisted labs that you can do in your own account. So make sure you have that. Okay, so we're going to talk about databases next. Here's one thing I want you to just kind of put into your brains. Amazon typically makes services for the most popular database technologies that are out there. So before I even get into this, I want you to tell me something, or like the most used database technologies. Give me some open source database technologies that you use or have heard about in your daily exposure. Give me one or two or three.
Postgres.
Right. So Amazon has an RDS service that has Postgres, MySQL, MariaDB, and Oracle, right, out there as well. What's another database technology that people use? Really popular. Could be anything that you deal with on a daily basis.
Like document database, like Mongo and Couchbase.
Yes. So they don't have a Couchbase service. I don't know why. Maybe it's a licensing thing. But they have a MongoDB service that's called DocumentDB. They also have Cassandra. It's called KeyStore. By the way, anyone use a graph database for anything? I don't know why I was expecting Catherine to become. Yeah, we've done stuff with graph. Neo4j, by the way, is a very popular graph database. Amazon has a service for that called Neptune. What do most people do for logging? Where do most people stick their logs nowadays? If they want to centralize logs from servers and applications, where do they stick those logs typically? What data store do they put that in? Could be Solar. So Elasticsearch is probably the most popular search database that people stick their log files into for centralization and searching. They use Kibana or that to search, right? So when we get into this, just so you know, Amazon typically makes services based on open source analogs. So Redis and Memcache, which is something you all saw earlier in the diagram, those are all part of the equation. So let's get into this. So RDS, which is that little gray box at the bottom, that's the relational database service. That's where your MySQL, your Postgres is. That's where all that is. And then Memcache, which we'll eventually get to, is the caching layer. That's also another database service, and there's a Redis version and a Memcache version, right? So just know that there's going to be an open source analog for almost every service inside of AWS. So here's the thing, though, is that running databases is quite frankly a pain in the rear, right? Not because they're not worth it; they're totally worth it. But care, feeding, there's a level of complication with databases, and sometimes you don't necessarily have the specialized skills. You don't have a DBA, right, or some kind of data engineer, data developer sitting around just waiting to manage your databases for you, right? So just know that we're mainly only going to talk about RDS, DynamoDB, but there's a ton of database services out there. Some of them, by the way, are not listed under the data store section. They're listed under analytics. So just be mindful. So let's talk about some considerations, right? Because we want a database that's highly available and scalable. Okay. Now, when you're choosing a data store, there's obviously there's typical criteria. One, are you using the SQL or you're not using? Are you using SQL or you're not using SQL, right? Do you need high acidity and high transactional base? Are you doing analytics? Or is it just a leaderboard and you just need something that you can write to and read from really fast? Maybe you're storing things as documents and you're doing search, or maybe you need a columnar key value store like Cassandra that can actually do replication, across different regions, for example. So we pretty much know our criteria because it's really dependent upon our use case as to which data store we're going to use, right? Scalability is a big thing. Because if you got a write-heavy database, just to say this, I know this is going to sound controversial, but your traditional RDBMS is not going to handle being write-heavy a lot. If you are at 80% writes on your relational database service, there might need to be some like additional sharding or some other kind of like shenanigans that have to happen to make that function. Because most RDBMSs, because of their focus on consistency, unless you want to throw a lot of horsepower at it, they're not going to handle that very well, right? But by contrast, the less consistent, not in terms of durability, but just less consistent overall from a consistency standpoint, NoSQL systems may make a lot more sense, especially if there's like a high change rate against the data, right? So it really depends. What are your scalability needs? What are your total storage requirements? What is your object size and durability? Like, what are you trying to achieve with your data? So total storage requirements, object size, like, are we talking about tiny little 256K bytes? Or are we talking about massive data chunks because you decided to store binary files in your database, which is not awesome? Maybe you're looking for something with lots of durability and recoverability, right? And maybe you have regulations that require you to replicate globally, right? Or at least outside of a region. Now, I've been referring to non-relational databases and relational databases because it's not like it's an us or them kind of situation. In most scenarios I work in, there is a primary source of truth, which is usually a relational database. And then there's either associated NoSQL databases or search databases, typically all three that make up the application. And in a microservices world, by the way, every microservice, if it needs state, has its own database. You might be like, that's horrifying, Michael. Why did you say that? It's like, well, that's because when you're operating at cloud native scale, everything's got to be loosely coupled, right? So you can't have a bunch of microservices sharing the same database. That's not going to work. You can't independently deploy, release, and manage and scale that way if three microservices are talking to the same database. Now, don't get me wrong. If there's two microservices that need to access data that another microservice is representing, those services can just talk to that microservice, but they're not going to get direct access to the database. So it really does matter whether you're using relational or non-relational, because relational databases typically scale vertically and non-relationals typically scale horizontally. And so, and if you're using SQL, you've got to use a relational database. Don't get me wrong. I know that some of the non-relational databases can use SQL, but they're not designed for that. So it's not ideal. A relational database does the table thing. This is like the same setup that we've been using since the 70s, right? This relational table structure where basically it's like, look, we've got columns, we've got rows, and those columns and rows each represent discrete individual types of data. And we'll have other tables that also have columns and rows. And typically there'll be like a foreign key that will refer back to a primary key, or some other section doesn't have to be primary key for the particular field in question. Because probably the primary key on this top table is the ISBN number because it's supposed to be unique, right? So you can, but there's this relationship between the table data sets inside of a relational database. And the database makes sure that data stays consistent from a write perspective, right? Now, if you need strict schema rules and data quality enforcement, and you don't need extreme write capacity in particular, because you can get really extreme read capacity off of a database, just to be clear. Off of a traditional relational database, if you add readers, like read replicas into a database, you can get extreme read performance off of a database, but you're not going to get extreme write performance. So if you don't need extreme performance, an RDBMS is going to be good for you. Now, compare that to a non-relational database, which says, I'm looking for this key, and then I just want you to return to me a blob of data, right? Now that blob is structured. I can find like ISBN numbers and titles and author and format. I can even search and filter off those attributes. So it's not like I can't filter queries, but I want you to just simply find it based off whatever key value. In this case, the key is probably the ISBN number because that key is unique. And so it's really important that keys are unique in the key value source, which is non-relational databases. And so you choose a non-relational database when you want your data, your system to scale horizontally. You want to read and write frequently and fast, right? But you don't necessarily need the strict acidity or consistency of a transactional database. You don't mind if the data is a little fuzzy on occasion, right? So, and again, you want a more economical read-write throughput that can be supported by a traditional database, right? That's what non-relational databases are really for. By the way, is it just me, Or I don't remember non-relational databases existing prior to 2000, 2001. Does anybody remember back that far? Or am I just like old? No? I was going to take that one. I don't really remember there being a lot about non-relational databases like NoSQL prior to like 2002, 2003. Yeah. Here's some some contrasting characteristics, right? SQL-based querying versus fixed querying, rows and columns on the relational side versus key value document and graph relationships on the non-relational side. Scalability is vertical on the SQL side, on the non-SQL sides, horizontal. By the way, they keep changing the language to go relational, non-relational, because NoSQL sounds combative. NoSQL doesn't mean no SQL, it means not only SQL. That was the original intention for using that term, was meaning that they don't use SQL language or structure to host the key value stored, right? Now, let's say you figured out what database you need. You know, it's a non-relational Cassandra or whatever. Or let's say it's a relational database. Are you going to roll your own? Because if you roll it on premise, you're responsible for everything that's in blue. If you do it on Amazon EC2, well, then all the infrastructure, server maintenance, and OS installation is handled for you by Amazon. But you're responsible for everything about that database, including operating system patching, database patching, backups, etc. If you do a managed service, which is what Amazon's RDS service is, the relational database service, they handle everything for you. The only thing you have to do is tell them when they can patch, how long do you want to keep backups for, what size of machine, and then all you do is manage the database engine. You don't manage anything else. You just optimize the app. Scaling can be a checkbox. High availability can be a checkbox. All of that can be handled for you, right? So this is where RDS comes in. So Amazon wants you to use managed services because this offloads a slew of concerns that, quite frankly, unless that's your core business, you don't probably want to get good at anyway. Now, Amazon has two flagship services, a relational service, which is RDS, and a non-relational service, which is DynamoDB. Remember what I said at the beginning. There are tons. There's at least 11, I think, database services out there on AWS. So just know they probably have what you're looking for. They don't have Couchbase, but they have Cassandra, they have Mongo, right? They even have Kafka, by the way, which is not really a data store. They have Graph, they have Solar, they have Elasticsearch, they've got tons of stuff. So here, by the way, is a little menu of all the stuff they have. RDS, Redshift, Aurora. Aurora, by the way, is a subset of RDS. I don't know why they call that out separately. It's a relational database service that you can actually start under RDS. It's not really a separate service, but it is an amazing subset. Notice that DynamoDB is there. That's a non-relational flagship database. That's flagship NoSQL. Elasticache we talked about. That's Memcache to Redis. Neptune is the graph database. And DocumentDB is basically a large MongoDB cluster with MongoDB compatibility. There's also Keystrokes, which is Cassandra. There's also Elasticsearch, which is Elasticsearch, right? There is Cloud Search, which I believe is a Solar kind of based system. What else is out there? I talked about managed Kafka already. There's a blockchain-based ledger database, QLDB, which is I would have never thought that would be a thing, but there is. Highly secure, right? And there's others. There's not coming top of mind right now. Actually, let's go look at the console. Dun, dun, dun. Dun, 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 dun. Let's go look at all services. Let's go look at our databases. So RDS, DynamoDB, Elasticache, Neptune. There's the ledger database. There's DocumentDB. Oh, TimeStream. Forgot about TimeStream. Time series database. So if you want data to come in and have checkpoints on time, TimeStream is awesome. The rest of the services are underneath analytics. So there's the data warehousing service. This is Redshift. Cloud Search is their older kind of Solar-based system. There's Elasticsearch. There's managed Kafka, by the way, MSK. I feel like there's one more. They're like hidden over here. So, but these are the popular ones. questions before I move on? There's going to be a quiz later. Unfortunately, there's no prizes. If we were face to face, you would have so many stickers right now, but unfortunately, I can't give prizes. Okay, so let's talk about RDS and DynamoDB, unless anybody has any questions.
Okay, I have one question. If, for example, you mentioned for Couchbase, there is no service, right?
Right, no managed service.
Yes. So if someone wants support from Amazon, they will provide, or like AWS, they provide this type of support, or like they will suggest to like go to MongoDB.
So what you would do is you would run Couchbase on an EC2 virtual machine, and
Yes.
you would be responsible for supporting the Couchbase instance. They would help you with the virtual machine, but they wouldn't help you with Couchbase.
Okay. Okay.
Yeah.
Okay.
They don't do custom support. They literally just stay within their wheelhouse.
Okay. Okay.
I say that, by the way, and if you have enterprise support with them, they will actually help you. So like they might not help you with support issues, but if you come to them and say, hey, I'm thinking about running Couchbase in this kind of like architectural thing, they will definitely assist you. When you have enterprise support with Amazon, which is like the highest level of support you can get, you get access to a TAM, like a dedicated technical account manager, and access to the product teams. And the SAs that are associated with your account, they will help you with practically anything Amazon related. But they can't offer support because they can't be indemnified for that.
Okay.
Yeah. Good. Other questions? Sorry, I got hit by a car yesterday and I'm like feeling a little sore. First car accident in a while, actually. All right, relational database service. So I realized I just inserted that in there. I was not the person at fault for that accident. I got hit by another car. So it makes it sound like, oh, I get into a regular car accident. Anyway, let's talk about the relational database service, not my sore shoulders. So the relational database service is a fully managed service. By the way, with a click, you can go multi-AZ and you can spin up a reader, like a read replica for your primary database in like minutes. It's ridiculous. RDS is cool, even though it's kind of like an older technology set. And don't get me wrong, I'm not knocking it. RDS, relational databases are awesome. But like they've been around forever. And so even though they've been iterating and stuff, you wouldn't think that they would like evolve as quickly as they have. RDS on Amazon is just absolutely awesome. If you need SQL-based system, this is the one to use, right? Now, RDS supports MySQL, MariaDB, Postgres, and then MS SQL and Oracle. It will not do Oracle RAC, so it won't do clustering. It also won't do MS SQL log shipping. Actually, is that true? It actually will do a form of log shipping, but it won't do any clustering with MS SQL. But Aurora is a sub-flavor of those 5 database engines where they took Postgres and MySQL and they made it cloud enabled. How did they do that? They actually made it so it's cluster volume aware using EBS. And so it does this really cool thing where it writes data directly to the data volumes. And so other instances in the Aurora like cluster, if you will, reads off that volume, but the primary writes directly to all the volumes in the cluster. So, but because of that, if you take the exact same schema and data set off of like a vanilla MySQL system and you put it into Aurora MySQL, it's like 5 times faster. It's ridiculous. Same thing with Postgres. You take a vanilla Postgres and you put it into an Aurora Postgres, same data set, same schema, same query access patterns. It is like 3 times faster out of the box. Aurora, by the way, also has a serverless version, which, by the way, RDS bases its databases off of EC2 t-shirt sizes. Let me show you. Because you'll be like, Michael, that didn't make any sense. Let me show you what I'm talking about. Oh, yeah, good database running. So if we come in here and we want to start an RDS database, this is the RDS service. Notice I have a Postgres instance running already. If I create database, the first thing it's going to ask me is going to say, which flavor? Do you want MySQL, MariaDB, Postgres, Oracle, or MS SQL Server? I can also do Aurora, by the way. If I choose MySQL, it's going to ask me for my version, right? Notice that we went from 5.7 to 8. Anyway, moving on. And let's say I want to do production. After I answer a bunch of questions about passwords and stuff, the next thing it's going to ask me is what kind of EC2 instance do you want to use? This is important to know, by the way. This is based off of EC2 instance sizes. So if we go back to our awesome website that lists all of our EC2 instance sizes, I want you to note that in this upper left-hand side for this URL, that there's an RDS tab. If I click on the RDS tab, it will tell me the database sizes that are available to my RDS instances. So if I'm out here and I'm like, look, I need a 16 gig RAM database system, it will give me all of the t-shirt sizes of EC2 instances that are associated with RDS that I can get to 16 gigs. So then I can go back to RDS and say, look, I need a DBT3X large. And so I can say, look, I'm going to do the burstable class. I need a DBT3X large. See what happened there? So know that RDS is based off of a limited subset of EC2 instance sizes. Aurora is exactly the same, but if I go into Aurora and I say, look, I want to do serverless, the serverless version of Aurora doesn't use EC2 instances underneath it. It runs completely hidden from you. So just know that there's a serverless version of Postgres and MySQL called Aurora that you can actually run as EC2 instance mode, or you can run it in serverless mode. Serverless mode means you only pay when a transaction is run. Whereas with any of these other database engines or provisioned Aurora, you are going to pay 24/7 for that instance that you run, which may be totally worth it. I'm not knocking it. I'm just saying that you are going to have to pay for that instance. So you might want to think about serverless if it's a non-production workload. Serverless, from my perspective with Aurora, is maybe just a little bit further away from production ready. But if it's a non-high intensity workload, like a non-production workload, you might want to consider running serverless Aurora, especially if you're using MySQL or Postgres. If you're using Oracle, Microsoft, MS SQL, or Maria, you don't have an option. You have to run plain vanilla RDS, which is good. I'm just saying, you have more options if you're using Postgres or MySQL. Does that make sense to everybody? About how RDS runs? You actually have to run it in an EC2 instance unless you're using the serverless version of Aurora. Any questions about any of that?
Just one thing. You mean like whenever we want to if you're not using Aurora and we are using this RDS service, then we have to pay for EC2 plus that service, right?
Yes, right? Because it's
Both.
virtual machine based. You have to pay for an
Yes,
EC2 instance. Yeah.
Yes. Okay.
Like here, you see that I have a Postgres system and it's running basically a DB, like a T3 micro in USE's 2B. So I'm actually paying for that virtual machine right now. If I went in, oh, go ahead.
Yeah, if you're taking that RDS service, they don't give any discount or something, like you're taking this service, so EC2 will be like for this service to be of lesser cost, nothing like that, right? You have to pay for EC2 and then that.
Yeah, so you can actually get reservations against RDS instances, so they're actually cheaper on a per hour basis. So I don't know if I'm answering your question fully. You will pay per instance. You can't actually get cheaper versions. If you want the cheapest version, then you're going to need to use Aurora.
Okay. Yeah.
Which means you're going to have to use Postgres and MySQL. Actually, I'm probably actually going to create just a quick instance. Oh, there's 5.7. Interesting. Here's a database. Here's the admin password, right? We'll confirm the password. You can set capacity settings like, do you want 2 gigs of RAM and or like it? Aurora serverless will auto scale to match whatever your queries are. I probably don't want that, just because even though I get a bunch of free credits from Amazon, I don't want to have to pay for more than just this. So I'm just going to limit it to 1 to 4 as far as scaling units. It's going to run, and I want it to run into a VPC that I created, and I'm going to create a new subnet group. I'm going to choose an existing security group, in this case RDS Michael only. Hello. Maybe I'll create a new one. See what it does there. And then we'll just create a database and see what happens. So now it's creating a serverless, and notice that this serverless is not region specific. It's actually, I mean, sorry, it's not availability zone specific. It's running across the entire region, right? So that's it. It's just that simple. Create a database, and notice it's creating right now. So Aurora is a subset of RDS that is Postgres and MySQL focused, right? By the way, Aurora databases can globally replicate. They're actually pretty cool. There's other things they can do even if you're not using the serverless version. So just be aware of that. Now, when would you use RDS? Well, anytime you need a relational database, that's when you would use RDS, right? You want to do analytics, you want to do transactions, it's all there, right? Now, that's all about RDS. That's your traditional database system. What about NoSQL? So NoSQL is a little bit more advanced in that it's a non-relational database service, and DynamoDB is the flagship service. This is event-driven. It scales horizontally. It is fully managed. The only thing you need to do is create a table, define your sort key, like your primary key, if you will, your partition key, and then you can just add data in, and it doesn't care what you do to the schema. There's no schema here. This is flexible schema. So high data volume, scalability. By the way, this, since it operates in a serverless manner where tables are the core unit, you just turn the dials on what you need and just go to town. That's it, right? You can globally replicate data across multiple regions back to a central, like kind of ephemeral table, if you will. Not ephemeral table. That's a weird statement, Michael. It's a global table, not an ephemeral table. But it's a centralized table that everybody replicates with in AWS. Great use cases for like gaming, social, leaderboards, scoring, session information, shopping carts, right? Great. So you can actually have your application servers writing back to a DynamoDB leaderboard or session state or shopping cart. It is awesome for that. Here's a shopping cart example where you've got multiple users hitting a web store. And by the way, if that means if a web server crashes, when the user comes back in, the web server, when the user reauthenticates, it'll just go grab the session information and say, hey, here's your shopping cart. We still got you, right? You can, by the way, either be strongly consistent or eventually consistent with DynamoDB. In other words, you can make it that you're like, hey, I only want you to answer this query if every replica agrees that this is the value. So you can actually make things strongly consistent versus lightly for eventually consistent. Just note that you'll get twice the performance out of your little compute units if you're eventually consistent, but if you're strongly consistent, you'll get exactly that performance. So DynamoDB, just to digress a little bit, if you go in here and you create a table, like here's a Terraform. I got a Terraform lock running because actually I have Terraform running to lock everything down. Terraform actually has all of these workspace examples inside the kit. Hold on, close this. You. Hold on. There we go. These are state files. So when I use Terraform to create infrastructure, here's one for a couple of different workspaces. Here's a global like workspace. But Terraform actually has like items inside of it. Here's the lock. The lock ID is actually the key. Here's a test key. This actually doesn't have any data in it. But notice that primary ID is actually the key. I can add any number of attributes to either one of these tables, and DynamoDB will auto scale to match whatever my demand is. So you can actually specify the read and write capacity of your tables inside of DynamoDB, or you can just say, look, I want you to go as fast as you can if I need it, or as slow as you can if I don't need it. You only pay for queries that are run, so you don't really pay for, you pay for data that's sitting here, but if there's not a lot of data, it's trivial. But know that in DynamoDB, you query a table, you query a certain partition key, and when you match that key, you retrieve all of the attribute data associated with that key. So this is really kind of a blob key value store. Really simple. This can be globally replicated, which you see global tables, right? You can set alarms. You can look at metrics. You can set capacity. You can create in-memory indexes if you want. So just know that DynamoDB has a lot of features to it. Now, what about security controls? So we talked about RDS. We talked about DynamoDB. We've got these characteristics to them, like, no SQL versus, SQL-based systems. What about security controls? Well, here's some interesting things. Databases can be made public. Most of the time, they're kept private, right? You can encrypt data at rest, and by default for DynamoDB, it is encrypted at rest. But for RDS, you can turn that on. You can also, by the way, turn on transparent data encryption for Oracle and MS SQL. So if you need TDE, you can also do that as well. You can actually force SSL to be on for all connections into the databases if you want to. So you can actually make that happen. And by the way, just know that there's a firewall that's wrapped around the database instances. So if someone tries to get in, they can't unless you punch a hole through the firewall. You can also receive event notifications if someone changes something, if someone changes security controls, if traffic is unencrypted, if someone drops a table, deletes a table, updates a table, you can set all kinds of event notifications for RDS. For DynamoDB, it's even worse because it's a highly managed service. You can define permissions down to the attribute level on a particular row. So you can control what a user can see all the way down to the attribute, like row level. DynamoDB is automatically managed at full encryption at rest. Everything by default is connected to TLS SSL. So you can't even turn that off, actually. And then you can actually encrypt using your own customer managed keys if you want to, if you don't want Amazon doing the keys on the back end programmatically for you. So, yeah. Questions about RDS or DynamoDB? Okay. So last thing we're going to talk about is the database migration service. So DMS is this awesome, and it's part of a family of migration services, just so you know. So if we go back to the console, just know that there's a whole series of migration and transfer services underneath AWS, including the application discovery and an application migration service. There's a database migration service and there's a server migration service. And by the way, the server migration service, by the way, will replicate your entire data center through agents if you wanted to. So just know, and it will actually support DR and all these other kind of cool features. So this is actually, you're not going to let me go back? That's weird. So the server migration service is also pretty awesome. Note also that there are other kind of like migration-y type services. Like you can do like automated transfers, you can do data syncs if you want to sync data. But for our purposes today, we're only going to talk about the database migration service. But just know there's tons of other services underneath here. Now, the database migration service basically can be used to migrate databases between RDS, S3, on-premise, and EC2 into a variety of different locations, and it can be used one shot, or it can continuously replicate data into AWS. So, just whatever you need in that particular aspect, right? You can do it one time, you can do ongoing. If the DMS service, because the data set's too large, you can actually set a checkpoint using like a snowball, copy it up to the snowball, and then push it out to and put the snowball back into AWS, restore the database, and then just do a sync, like almost like an incremental checkup or verification to catch up your on-premise database. I'm sorry, your EC2 database with your on-premise database. So the migration service can be used in conjunction with the snowball to move a very large data set into AWS. So, by the way, the snowballs are usually 50 to 80 terabytes used for migration. They can also host compute and other things, but you can actually sync your database with the edge, put the edge in AWS, and then replicate anything that is a differential at that point in time. There's also a schema conversion tool that's part of the DMS service that will help you migrate from, say, MySQL to Postgres, or Teradata to Redshift, or Oracle data warehousing over to Redshift. There's actually a huge list. It's like Greenplum, Teradata, DB2, for example. And by the way, it doesn't just have to be SQL to SQL. You can actually migrate from SQL to NoSQL as well. So it'll help you port that data over. So the schema conversion tool is actually pretty cool. I've used it, and as long as it's not a super, I've seen some really complex like stored procedures and whatnot, and they all transfer over. I'm not a data specialist, so don't take this as just like an infrastructure guy having to do data transfer, right? But it seems like if there's more complex joins and weirdness, customizations of the Postgres, for example, adding weird extensions and investments, things tend to break. But I'm shocked at the amount of successful conversions we've done with the schema conversion tool and DMS. Questions about anything DMS, anything DynamoDB, anything RDS at all? Cool. All right. Let's talk about our next lab. Wait, I sound like I have a question.
Yes. About the migration service, like how actually behind the scene it works. Like if I am migrating from relational database to the NoSQL, maybe DynamoDB. So how is going to work? Like I put the input, like I give them my database, all the relational database information, like these tables are there and everything. So like how it's like automation, or like behind the scene AWS, someone from AWS, like AWS engineer will do this.
Oh no, it's all automated. There's never an engineer involved in any of AWS's processes. They're always automated. So it actually does an automated kind of like scan. You put an agent on the system, it puts very little load on your database. It scans the tables and then starts replicating data based on what you specify. And the schema conversion tool in particular will identify the schema translations and let you modify it if you feel like that going from a table to another table, it's misidentifying it. But the DMS service itself is agent based and it's fully automated.
Okay.
Yeah, there's no engineer. It's not a like a consulting service. Everything AWS is all automated. Okay, so let's talk about deploying a web application on AWS. So we're going to be basically touching the firewalls, which are security groups. We're going to be touching RDS, which is the relational database service, and we're going to be touching the virtual machine, right? So your labs are pre-warmed. So you've got a VPC across 2 availability zones, 2 public subnets, and 2 private subnets. The difference, by the way, is whether the internet can get to that subnet or the internet can't get to that subnet. That's the difference between public and private. And then we've got a security configuration, which we've got an app security group and a database security group. Those are 2 different sets of firewall rules, right? And then you're going to deploy a database server and an application server and then test the application, right? This is about a 30-minute lab. We're going to give it a little bit more time, right? Maybe like 35 minutes or so, right? But you want to work pretty intently on this lab because they kind of make these like short and intense, right? And let's go take a look, if you will, at the quick labs. So it looks like there are 7 labs that are still pre-warmed for lab 2. And so if you open up this lab, if you've logged into webage.quicklabs.com, and I'm going to post this in again just to make sure that you have full access. If you have the right URL. But once you log in, you hit Start Lab, and it's going to immediately give you the console information. Make sure that you have closed all of your Lab 1 windows because they are invalid. That lab is ended. It's closed. If they're still open, close them. But you're going to open your console into US West 2, and then all the directions are right here on this primary lab page. Everything you need. Okay. So we're taking about at least 30 minutes. So it's 2:25 Eastern by my watch right now. I'm going to let you go. You're going to work on lab 2, and I'm probably not going to check back in until right at 3 o'clock. And then we're going to roll into the next set of things, and then we're going to end with the lab for today, right? So go ahead and get working on lab 2. Go ahead and hit that start button if you haven't already done so, and just go ahead and start following directions. Remember, you want to put on your detail orientation hat and make sure that you are following the steps. If something's missing or something's changed, let me know. I will take a note if the instructions are slightly off and make it more readable. But for the most part, these labs are pretty battle tested, so they should work for you. Okay? Go forth and conquer lab 2. I will be here, not going anywhere. covered basic, like where services live as far as a region, availability zones, local zones, and edge locations. We then touched briefly on S3, including the 3 ways in which you can talk to AWS, which is the console, the CLI, or the software development kit. And then we spent some time on compute, talked about EC2, the different licensing types for EC2, how AMIs work, how user data and instance metadata works inside of EC2, the different disk drives, including EFS, which is actually a network file share, versus the direct attached drives that you can attach. And then we just talked about databases and spent some time talking about RDS and DynamoDB, and a little bit about the database migration service, just so you're aware that it's there. And now we're going to move on to networking. Now, if I was the emperor of AWS, I actually probably would have started off with users, then networking, then storage, and then gotten to compute and networking. But just know we're going to spend both this afternoon and tomorrow morning on networking so you can understand the basic concepts around VPCs and subnets. This does get a little heady because there is some CIDR notation involved in this. I'll do my best to try and visualize that as much as possible. Just note that if you don't get the CIDR notation part, it's okay, right? There's plenty of subnet calculators and other tools that will help you figure out how to partition your networks, which is usually what people get hung up on. Okay. All right. Networking part 1, here we come. Okay. We do have a lab in the middle of this particular section. So when we finish part 1, we'll actually move on to the next lab. I will go ahead, actually, I guess, start that. Let me make sure it's all ramped up and warmed up here. Here we go. All right, excellent. Okay, so this entire time that we've been doing EFS and RDS and whatnot, we've been sitting on top of networking, but not S3, because S3 is a managed service that sits outside of that. So is DynamoDB, by the way. But we really haven't talked about what VPCs are, what subnets are. We kind of touched on them briefly, what the role of an internet gateway is, and then what a role of a NAT gateway is for private subnets. So we're going to talk a little bit about that. That's going to be what we're going to cover now, is VPCs and whatnot. Now, the need that you're trying to solve for is you've got to design a service that allows you to deploy and manage like AWS resources in a networked environment, and you want to provide some level of either product or application service isolation. This is where virtual private clouds, subnets, gateways like internet gateways and NAT gateways, and network security becomes paramount. Because first and foremost, AWS is a security company, right? They provide security in the cloud because it was the #1 objection and has been the entire time. Can you imagine the treasure trove that hackers are always looking for here, the gold of all these companies running inside of AWS, and they're just looking constantly for misconfigured firewalls and networking. You know, it takes about only like a couple minutes if you actually post something, say on like GitHub that's public, for it to get picked up and used against your AWS account. For example, if you stick keys in a repo. Amazon's done a good job, by the way, of also doing concurrent overlapping scans of GitHub, so they actually will lock down your account if you accidentally post your AWS secret user and secret keys inside a repository. So they'll help you as well. But that's the need, is we need to create an isolated networking segment, right? So that we can isolate our workloads, do least privilege for users, and make sure that not everybody has access to everything. This is where virtual private clouds come in. Virtual private clouds are networking partitions that sit inside your AWS account. They are region specific, meaning that they encompass an entire region. They provide logical isolation, and they do allow for custom security partitions and other isolation metrics. Sorry, mechanisms. Other isolation mechanisms for your account. Now, it is a virtual network. It does require an IPv4 space. What kind of IPv4 space? The same networking numbers that we use for our home networks. We use 10s, 192.168 for our home network, and we use 172, either 16 all the way up to 172.32 for our networking ranges. This is from RFC 1918. So RFC 1918 is an internet tool that basically says these are our private network hosts. Now I'm not going to go through this entire thing, right? But this basically says, what are the RFC 1918 addresses? Well, they're here. These are the RFC 1918 addresses, basically 10 all the way through, like everything 10, 172.16 to 172.31. And then basically 192.168.0.0 all the way out to 255, right? These are our private address spaces. So when you create a VPC on AWS, you have to tell it what kind of network you want to use. Typical recommendation, make it as big as you can. Make it the biggest network that you can support because you don't want to run out of IP addresses. So just know that you need an IPv4 space to make this happen. And you can control inbound and outbound access. You can control routing. You can put firewalls up. You can control a lot once you have a VPC. Now, when you deploy a VPC, it eats an entire region, right? By default, Amazon has created a default public VPC in every region that you have like open access to. So the VPC, by the way, can host resources from any of the availability zones that are in that associated region. So just be aware that a VPC is region spanning. Now, typically people don't use just one VPC. If they go for a multi-account model, they might have multiple accounts, and each of those accounts might have a VPC in it. But typically each account is going to have from 1 to 5 typically VPCs in it. Most people don't run 15, 20 VPCs in a single account because it's not effective from a quota perspective. Do note that when you want everything tightly coupled, when a VPC is awesome, and if you want to simplify identity management, it's not really VPC specific, it's actually account specific, but most of the time we run multiple VPCs. There are primarily two ways of organizing your AWS usage. You can either have multiple accounts, like one per team or one per product, or you can do one VPC per team or per product. Most people do not do multi-VPC. Most people do multi-account. It just depends on the size of the organization. Enterprise organizations tend to go for multi-account. Smaller organizations will tend to go for VPCs, but if they have more than one product, I mean, I've worked at like, $5 million companies that had, 5 AWS accounts. Each product had its own account, right? Which is actually pretty awesome. The multi-VPC pattern is for single team or for simple organizations, right? This is when you just have multiple VPCs inside of a single account. Governance and compliance, might require greater workload isolation, but that's usually pretty simple to figure out. Scale is the problem. If you're large, you're going to go to multi-account. You're not going to do multi-VPC. So multi-account is going to require you to manage accounts en masse, which, by the way, is probably going to have you using AWS Organizations, which is a service that is designed to manage multiple AWS accounts under one primary account, the primary organization account. So, multi-account is good for anybody medium size and above, right? That's typically the standard. Now, you can only have, by default, 5 VPCs per region per account. You can actually go into something called the service quota dashboard. Let's not mess with that one. Let's mess with this one. You can go into what's called the service quota dashboard, and you can actually come in here and you can request an increase on your service quotas. For example, here's VPC. If we click on VPCs, you'll notice that you can only have, let's see, where is it at? Internet gateways, gateways per zone, security groups. Here it is, VPCs per region at the very bottom. By the way, service quotas are inside every AWS account so that you can't financially hurt yourself with AWS, nor can a hacker. It's also to prevent you from wrecking AWS as well, right? Can you imagine if you came in here and you accidentally spun up 20,000 machines? By the way, if those were $1 a piece, you just spent $20,000, right? Which could be problematic. But AWS doesn't allow that, right? Just so you know, you can only spin up maybe 300 virtual machines right off the bat. Usually it's 50, depending on the type of system. But These are service quota limits that you have in your account, so you can't just en masse spin up a bunch of infrastructure, but nor can someone accidentally on your end spin up a bunch of infrastructure. So here, VPCs per region is actually considered, see how that yes is right next to it? That yes, by the way, refers to adjustable. So you can actually come in here and say, like right now, I've got 5 VPCs per region. I can actually come in here and say, you know what? I want to request a quota increase. I want to actually go, up to 10, right? And I can request that my quota go up to 10. Amazon, this one, by the way, is automated, but they're gonna run a quick little analysis against my usage pattern inside my account, and it'll be all automated. And if the automation's like, nah, there's no red flags here, it will actually approve my request. And I can actually see that because there's like a quota request history, and it shows pending, right? That I just asked for an increase in regions per system. Not every quota is adjustable. But by the way, when you do multiple accounts instead of multiple VPC, you don't usually have to worry about the number of VPCs that you have inside of an account, because when you're doing multiple account, when you need to start another like product or another team, you just open a new account and then put that in your organization. And now you've got a whole different set of account limits. You get a new set of account limits if you go multi-account. If you stay within the same account and you open multiple VPCs, you will hit a lot of limits eventually as you scale. So just know that VPCs typically stop at 5 per region per account, and that you can request more if you want, but most companies are going to do a multi-account strategy, not a multiple VPC strategy. Now, when you request a VPC, when you go and create one, you have to give it an IP range. So if we're out here, for example, under VPC, and we decide that we're going to create our own one out here on the console. First of all, there's a wizard. So I just want you to know there's a great wizard for VPC. So if you click on the VPC launch wizard, it'll say, hey, do you just want one with a single subnet? Do you want public and private subnets? Do you want hardware VPN access? Or do you want only a private subnet with hardware VPN access? So typically most people do public and private subnets. You can select this. You can change these IP addresses. So notice this says a 10.0.0, that's 0/16. That means this is the network. These are all the host addresses that I can use. /16, because each of these is worth 8. A /16 means 8 plus 8. That means that's the network. These are the hosts. And these numbers can run from 0 to 255, but if this is the network, this can't change. That's what this /16 means. It means 8 plus 8 can't change. This is the network. That number, 10 and 0, defines this as this network. But the other 2 zeros, they can go from 0 to 255. It's totally fine. Notice it's telling me that if I do this, I'm going to get 65,000 IP addresses. If I drop this down to 15, guess what happens? Oh, it says you can't do that, Forrester. This, by the way, figures on the exam. If you're going to take it, your net mask, that number that's at the very end, this after the slash, has to be between /16, 17, 18, etc., all the way to 28. It can't be 29 and it can't be 15. It has to be 16 through 28. So if I drop this down to 17, which is a legitimate number, look what happens. Ooh, not 7. That's not going to work. Not 187 either, because that's not going to work. But if I drop this down to 17, notice that I have my host addresses. So the number of computers I can stick on this network is now half. If I drop it down to 18, guess what happens? That number halves again. If I drop it down to 19, the number just keeps on halving. Most of us do this in our home networks. Ignore all this stuff that it's complaining about, right? Right here, what I've done is I've actually said 8 plus 8 plus 8. That's the network. That's what a /24 is. /24 says the first 8, the second 8, and the third 8. That's my network. So this is going to stay unchanged. But that means I now have 255 minus what Amazon has to take, which is 5. I have 256 addresses. I'm going to take 5 off. Sorry, 256 addresses, not 255. So I'm taking 256 addresses and I'm taking 5 off because Amazon needs 5 to run the network. but that's CIDR notation. So I have to put from that RFC that we were looking at earlier, I have to put, because remember, we were looking at this, right? I have to either put a 10 address, a 172 address, or a 192.168 address in that box. And it can be within this range. So here I am, and that's what I'm doing, is I'm putting a 192.168 address in this box. That defines the networking information of the VPC. If I want to change this to a 2 network, I can make it a 2 network instead. Now here's the weird thing. I'm gonna actually switch this back to a 0. And I'm actually gonna change this back to a 16 because I want to make this as large as possible. And 16 is the largest number of addresses I can make. And notice now I've got 65,000 computers that I can stick on this network. Now, this is all my networking information. What happens is that I've got now defined a VPC pie, and I've got to put subnets that are slices of that pie. Subnetworks are called subnetworks because the VPC is the major network, and the subnets are slices of that VPC pie. So it's really important that when down here, see how it says these are the public subnet, here's the private subnet. These have to be a slice of that VPC pie. So if I do 192.168.1.0/24, it's going to stop complaining. If I come down here and say I want to do a 192.168. Let's say I want to do a 2.0/. Oh no, let's not do that. Let's do a 5.0/23. Oh, sorry, 4. Sorry, I meant 4. Yes, thank you. My math was off. What this means is that this public subnet is going to end up with 251 usable addresses. Why? Because with a /24, that means only this number can change. And that number can range from 0 to 255. That's 256 numbers if you include 0 as a number. Amazon's going to take 5 because it has to manage the network. And so I'm going to lose from 256 minus 5, I'm going to get 251. Now, down here, I shifted this a little bit, and instead of doing 8 plus 8 plus 8, I did 8 plus 8 plus 7. So I only actually wanted a fraction of this little number right here, which means that now this is a 23. And so now instead of having 251 addresses available, I have 512 minus 5. Why 5? Because Amazon has to take 5 to manage the network. But notice that this was 256 and this was /24. At /23, I'm dropping to 5. I'm doubling to 512. As this number gets lower, this number keeps doubling. If this was a /22, which by the way, Amazon's going to complain about that, then this becomes 1,024 minus 5. That's double 512. If this drops to a 21, what's going to happen is this is, nope, I did not actually. Hold on. This is going to go to 2048 minus 5. What's going to happen, by the way? What's going to happen if I drop this number down to 20? If this was 2048, because it's 243 plus 5, what's going to happen to this number? Is it going to go up or is it going to go down? Hello? Can everybody hear me?
It's going to be up.
It's going to go up, right?
Hmm.
So if I drop this down to 20, this would jump up to 4096. But now, by the way, it's complaining about the number. So I'm going to actually run this up to 12. Actually, you know what? That's right. Let's leave that and see what it does. There's a bunch of math here that I need to do, and I don't really want to do it actually because it's going to make things complicated. But the bottom line is that I'm going to keep this at a /23. Put this at /4 because that's all the IP addresses I need. Notice that my private subnet has more IP addresses than my public subnet. Has a general best practice with AWS. Do not stick things on the internet. Stick AWS devices on the internet to act as proxies, but keep your stuff private and let AWS defend the devices that you have stuck out there on Amazon's behalf. I know that sounds weird, but that's the way it works with load balancers, right, and gateways. So notice I haven't asked for a different version of IP addressing. I'm just sticking with IPv4. But then this is how you would create subnets. Notice that also I can enable DNS hostname. And remember earlier, we were talking about dedicated instances. This is where you switch it to dedicated so you can actually start dedicated instances. But I'm going to leave it at default, right? I haven't given it a name either, right? But this is like Arch class VPC. Leave that as is. Oh, wait, do I have elastic IP? Hold on. I don't have an elastic IP address. Do I need one? Apparently I do. I guess I would have to request an EIP in order for this to go forward because it's trying to auto provision a NAT gateway for me, which I actually don't want because NAT gateways actually cost like a penny an hour and they add up over time. And I can't tell you how many times students have been burned by that, myself included. So remember, VPCs are a network segmentation of your overall account. Subnets sit inside of VPCs. And you have to typically use one of the RFCs that I just showed you, the 10 address, the 192 address, or the 172 address. Here's that class, like the CIDR, the class of subnet domain routing again. Notice that those numbers after the slash will tell you the total number of IPs that you have. Remember, at a /24, you've got 256 IP addresses minus 5. Every time you go up, the number halves. Every time you go down, the number doubles. So if 24 is 256, a 23 is 512. A 22 is 1024. A 21 is 2048. A 20 is 4096, which you can actually see right there. A 20 is a 4096. So you don't have to remember how many computers you can stick on this network. You just have to remember that a /24 is 256 addresses minus 5. And if you go up, have that number. If you go down, double the number. And that's really classless internet domain routing at its simplest. It can get more complicated because we're just kind of scratching the surface here. Now, once you've chosen your networking, you've got to create your subnets, which are slices of that whole pie. So for example, if you have a VPC that's a /22, which means you have 1024 total addresses, then what happens is that you can create a subnet with 251 addresses, another subnet with 251 addresses, and another subnet with 251. And if you keep going, by the way, and you add all those together, that's 1024 addresses. So remember, you are going to be constrained by the number and size of the subnets that you can create based on the total VPC network definition that you specify. Now, subnets are a subset of your VPC. They cannot overlap. You actually just saw it complain when I tried to make VPC, like subnets overlap. Subnets can't overlap. Each subnet, by the way, has to live in its own availability zone. Not its own. You can actually have multiple subnets in an availability zone. But a VPC spans the region. The subnets that live inside of a VPC must live in one and only one availability zone. Subnets cannot span availability zones. VPCs can span availability zones, but subnets, which are slices of the VPC pie, they have to live inside of a specific availability zone. Note, as I showed you before, AWS is going to reserve 5 IP addresses from each subnet. Now, once you create all these subnets inside of a VPC, how do they find each other? How do they talk to each other? Well, just so you know, by default, subnets can talk to each other, assuming the firewalls that are allowing the traffic. Subnets can talk to each other all day long, right? They can have conversations with each other if they're in the same VPC. You can disable that easily, right? But they assume that you want to talk inside the VPC network. You don't want to isolate traffic, but you can easily change that. Now, associated with every VPC is like a map called a route table. The route table tells everything inside the VPC where to find everything else. If you want to have a custom map or route table associated with your VPCs and you don't want to use the VPC's route table, you can actually create custom route tables inside your subnets. That way subnets can either isolate themselves or they can find other subnets. They can even find the internet, or they can even find your corporate network if you have a VPN connection or a direct connect connection to your corporate network. So these route tables are used to say, hey, I'm looking for the corporate network and I'm on the 10 network. And the route table says, oh, if you're looking for the 12 network, go talk to the VPN connection. Oh, you're looking for the internet? Go out through the internet gateway. Oh, wait, you're on a private subnet and you want to talk to the internet? Go to the NAT gateway, right? So route tables are used to say, hey, if you're looking for traffic, go here. And you can have a route table for each subnet individually, or you can have a route table for the entire VPC. So just know by default, the VPC's route table is inherited by all of the subnets in that VPC, but you can create your own custom route tables for each VPC if you want. Best practice, don't use the VPC's route table. Be intentional about using your own custom route tables for each of the subnets so that traffic is flowing exactly the way you want it to. That kind of enforces, in a sense, like networking least privilege, right? Now, subnets, by the way, will either allow you to talk directly to the internet. I'm not talking about natting either. I'm talking about direct routing to the internet. Or they're going to be private, which means they have no direct network connectivity. And if they want to talk to the internet, they have to use a proxy or, in a sense, like a representative on their behalf. Typically, this is the NAT gateway service, which means the private subnet, any computers on that private subnet will talk to the NAT gateway. The NAT gateway will go retrieve stuff from the internet on their behalf and then bring it back to them. So I guess it's not really a proxy. It's kind of like a translation layer. Now, if you want to connect a public subnet to the internet, all you have to do is add that little entry. So see in the center right there, just to say this, see this little thing right here, these blue arrows? That says if you don't know what the traffic is, because you only know 10 traffic. If you don't know what the traffic is, send it to the internet gateway. The internet gateway is like, oh, let me just send it out across the internet. I know where you want to go, right? So, and note the picture over here. You've got users who are coming into the internet gateway, who are coming in and they are getting to your instance, which not only has a private IP address, but it has a public IP address as well. This is important, is that without a public IP address attached to an EC2 instance, even though it always has a private IP address, if you don't give it a public IP address, it can't get out to the internet because the internet can't talk to it. So you actually need a route table entry and you need a public IP address in order to be able to get a box to talk to the internet. This is all over the exam, by the way. They will try and trick you and say, hey, this is the route table. The route table won't have a reference to the internet gateway like this, or they'll give you an instance without a public IP address. No public IP address, you can't route to the internet. By the way, that doesn't mean there's not firewalls here that can stop all this traffic. That's another factor. But mainly you need an instance with a public IP address and you need your route table to have access to the internet gateway ID for it to be a public subnet, right? If you want this to be a public subnet. Now, if it's a private subnet, which means that it has no route to the internet cannot see it and it cannot see the internet. What you have to do is you have to put a NAT gateway. You might say to yourself, Michael, why would I want to privatize a subnet and then somehow give it internet access? Would I just make it a public subnet at that point in time? No. The reason is that you want your resources to have indirect access to the internet because that way the internet cannot get to them, right? and Amazon will have to defend anything that's stuck on the fringe. So, but you still might want to get to the internet because you might want to download software patches, or you might need to retrieve something from another public location. So how do you do that? Well, what you do is you add a NAT gateway onto your private subnets. Now, here's the funky thing. No, this is the thing that's weird, right? Oops, sorry. Is that your NAT gateway actually lives over in a public subnet. So here's your NAT gateway, by the way. Here's your NAT gateway service surrounded by stars right here. Notice it's on a public subnet. But your private subnet down here, your EC2 instance, it is going to talk over to this guy. Actually, let me change my colors here, see if that works. Oh, you're not going to change colors. That's fine. So this instance is actually going to talk to the NAT gateway. The NAT gateway is going to talk to the internet. I just want to be clear. Users cannot get to your box through the NAT gateway. This is not for inbound traffic. NAT gateways are only for outbound traffic. So this is not a load balancer. You can't actually initiate traffic from a user into this system. You can't do that, right? Now notice here that the public route table actually has an internet gateway attached to it. And the private route table is doing the same thing, except instead of sending to an internet gateway like up here, it's actually initiating to a NAT gateway ID. That's the difference. They both have outbound access to the internet, but the public route table, also the internet can get to the systems that are on that public subnet. The internet cannot get to the systems, cannot initiate traffic into a private subnet. So it is protected from the internet. It can't get to it. So no inbound traffic is going to come in. You all with me? Am I losing you? Any questions or curiosities or concerns?
Trying to retain as much as we can.
Aren't you glad that for the most part in large organizations, you don't have to deal with this? I'm usually the guy who has to deal with this. But usually teams have networking, security, and operations engineers who will handle this for you. So in Booz in particular, typically that's the case. Oh, hold on, chat closed on me. Good. All right. Okay. Now, what are your subnet use cases? So really, by the way, just to say this, you're going to have subnets if you're going to run anything with a network card. And best practice, run everything you can inside of a private subnet. Try to put as little as possible on a public subnet. Because if you put it on a public subnet, you have to defend it, right? And so if it's a load balancer or a NAT gateway or some other device like that, guess who has to defend it? Not you. AWS has to defend it. If you use their NAT gateway service, that's a like black box service to you. You can't see inside of it. Amazon has to defend it. You use a load balancer, that's a black box service to you. Amazon has to defend it. You want Amazon to defend your public access and not have you defend your public access. So try not to put your web servers on public subnets. That's the old way of doing it. You want to put them on private subnets, put a load balancer in front of the web servers and let Amazon defend that load balancer. Their security team is awesome at defending their own infrastructure. So, let them handle it, right? So these subnet use case examples are horrible because it's going to be basically anything where you need to have a network interface, which could be a Lambda function, could be a container, is definitely going to be virtual machines. Or an RDS instance, because RDS uses virtual machines, right? Except for Aurora serverless. So you're gonna create subnets for what you need subnets for. Oh, I see this is a question. So data stores are going to go on private subnets. Batch processing is going to go on private subnets. Backend instances are going to go on private subnets. And guess what? Web application instances, no, they're going to go on private subnets. If you have to run them publicly, sure. But for the most part, the answer is no. You're not going to run anything publicly if you can get away with I said this before, make sure you go with the largest subnet possible. You can later on add another IP range to your VPCs. They call them secondary CIDR ranges, but that solves the problem, but it also adds a whole other set of problems. Now you got two problems. I'm just kidding. So try to go with the largest subnet range that you can initially, right? At least a /24 or 23 or 22 or 20 or 19 or larger, right? Try to simplify your workload placement as much as possible. So like having to figure out like where on 10 small subnets is more complicated than if you have one large subnet. You can run out of IP addresses. Even though these are private ranges, you want to try and keep things isolated as much as possible. And so you want to make sure you choose a big range that's going to give you plenty of opportunity to grow. Because it might not be in year 1, it might not be in year 2, but in year 3, 4, and 5, you're like, oh my God, I wish we had chosen a bigger pie for our network. Good. Here's the basic subnet configuration. One public, one private is pretty standard. The private's usually much larger than the public, right? In this particular case, you see a /24 and a /23, which is the exact same example you saw before with me. Notice it's showing a 10.0, a 10.1, and then a 10.2 and a 10.4. Because when you start shrinking the numbers on your subnet range, your blocks of numbers gets bigger. So you're going to need 2, for example. So 10.6 would be the next one in the /23, for example. Most of us, by the way, have far more private resources than we have public. So make sure your private subnets are pretty large. Now, I mentioned this before, is that Amazon has virtual machines that have elastic network interfaces on them. And adding more elastic network interfaces to a virtual machine, by the way, does not make it faster. But you can also attach network interfaces to Lambda functions and to containers, which they kind of already can contain, actually, especially if it's Kubernetes. Network interfaces can be moved to different machines in the same availability zone. So if you need to retain the IP address and MAC address for licensing reasons or whatever, you can actually just take the network interface off of the system. Only if it's the secondary interface. You can never remove the primary interface off of an EC2 instance. They always require that because otherwise you can't manage the instance. And so you can retain the MAC address, you can retain the elastic IP or any private IP addresses you've associated with the system. That's if you want to move the interface. If you don't necessarily care about, like you're not trying to increase bandwidth, you can put multiple network interfaces. So you can have one for like database traffic, another for, application traffic or whatever. Just again, adding network interfaces doesn't speed up a box from a network perspective. The box is always at its max. Now, if you don't want to move, you don't need to retain the MAC address. You just want to retain the public IP address. Well, you could just attach an elastic IP to the system. An elastic IP address is a static IPv4 address. So not a 10 address, not a 192, but like, for example, like a 54 address. And you get to retain that IP address and you can move it onto other systems. So like if ever a DNS is pointing towards an IP address and that box fails, and you want to keep DNS because it's too much of a pain, you can just move that IP address over to another system. Now that's a manual effort, which is kind of frowned upon. We better off to use a load balancer. But if you have that, you can. And you can, by the way, bring your own IP addresses into AWS. So if you own a public range and you want to use that inside of AWS, you can, actually. So just know you have elastic network interfaces and you have elastic IP addresses that you can associate with an EC2 instance. Let's see here. By default, you're allowed 5 IPs per region. You can easily request more. I've had 100 per region. As long as you use them, AWS doesn't typically tend to get too upset. They have run out before. Let me scratch that. They haven't run out. We've made bad requests for it, basically. But do note that you can have a main server and then you can roll things over to it like a backup, like a hot backup server. So here they're actually moving the IP address over. By the way, someone either say it or type it into chat. Where do you go inside the console if you want to request more IP addresses per region? What was the name of that particular section of the console? Anyone remember? Service quotas. That's where you go if you want to change the max of your quotas inside of an account. Okay. Interesting that you're allowed 5 IP addresses. You're allowed 5 VPCs per region. There's a bunch of other 5s in here for networking as well. Okay. Last little bit. What about security in the cloud? Well, understand there's 2 firewall types inside of AWS. There's stateful firewalls, which are known as security groups. There's stateless firewalls, which are known as network access control lists, or NACLs. Network access control lists are associated with the subnet that we were just talking about. Those subnets, those are subnet firewalls. Security groups are associated with network interfaces, and they're always present with an EC2 instance. So security groups are stateful firewalls that can deny traffic. They deny traffic by default, but you have to allow traffic. So by default, security groups say no to all traffic. You have to explicitly allow traffic for a security group to function. Security groups, by the way, can be restricted by IP address, by port, by protocol. In order to respond to initiated traffic, you only need one rule. What that means is that if you're allowing someone to SSH into your box, you don't need a second rule to respond to that traffic. You only need one rule. That's because it's stateful. So it watches the session come in and it automatically allows you to respond to the session. It won't allow you to initiate traffic anywhere else, but it'll allow you to respond to the session. So you don't need a second rule. With a network access control list, you have to have a rule to allow inbound traffic on port 22, and you have to have a rule to allow outbound traffic on port 22, because it's a stateless firewall. It's not a stateful firewall. Security groups are stateful. You need one rule to allow yourself to respond to initiated traffic. Notice here, there's this red box around the app. That's a firewall that sits around the virtual machine's network card, because it's the only way to get in, right? So it's a network-based firewall. Now, by default, no one can get into an EC2 instance. So if you put it on the internet, guess what? Internet can't get to it. The box can get to the internet, but the internet cannot get to it, right? So by default, security groups block all inbound traffic and they allow outbound traffic, which is great. Because if you need security patches, or you're gonna go do a Yum update or get Microsoft patches, you can do that and the internet can't see you, can't even mess with you. Now, how do you control traffic? Well, a lot of people will set it so that if you're in the web server group, the app server security group will only allow traffic from the web server group. If you are in the database tier will only allow traffic if you're in the application tier. Security groups, right? So you can chain security groups together to say, look, database, I don't only want you to take traffic if it's a server that's in the application security group. And application servers, I only want you to take traffic if it's in the web server security group. So you can actually really tightly link security groups together so that only boxes that are in those security groups can actually send you traffic. So here, you've got the web tier connected to the application tier, connected to the database tier. It's like, you got the ankle bone connected to the leg bone, and the leg bone connected to the knee bone. It's like you're tying together the web app and database tiers by saying, look, I'm only going to take traffic from members of the web security group. Has the database, I'm only going to take traffic from members of the application security group. And notice the allowed ports there, 443, port 80, 3306. Those are very specific ports. So it's not just all traffic, it's just that particular port of traffic. Now, we just talked about stateful firewalls. What about stateless firewalls? So while security groups wrap around the network card, access control lists wrap around the subnet. So they sit outside of the firewall for the interface, right? They're at the subnet boundary. Now, I'm just going to say this. By default, subnets allow all inbound and outbound traffic by default. Why? Because it's really complicated if you start blocking stuff at the subnet level and at the security level, the security group level. So what they do is that they allow all traffic by default. And what you need to do is that mainly people use network access control lists to deny traffic. Like, if you're only serving the United States and somebody, out in Kazakhstan decides to start hitting your server with a bunch of malformed requests, you can just go into the subnet and just block them. Say, I don't want this IP range talking to them. And then, what, the packet's just going to get dropped by the perimeter firewall. Now, notice that there's a rule necessary for both inbound and outbound traffic, and rules are evaluated in order of precedence. So rule 1 is evaluated before order 50, rule 50. Notice that there's an inbound and an outbound rule set. And as you can see here, this particular one is fascinating because this rule at the top basically allows SSH traffic from this particular source. By the way, note that there is no rule down here that allows 22 traffic to go out. Right? Because right now they're denying this traffic and they're denying this traffic if it doesn't match any rule above it. In other words, if the minute a rule matches the traffic goes through or it's denied, right? So in this case, if it's not from the 172 address and hitting these ports, then it's going to get denied. But if it is, it's going to be allowed. In this particular case, above, if it's port 22 traffic and it's coming from this specific IP address, because this is a /32, it's port 22, that's going to be allowed. By the way, the system can't respond because there's no port 22 rule down here that allows it to respond to this traffic. So this rule is kind of half broken, frankly. And so what will happen here is that if it matches a rule up above, then it won't necessarily hit this rule next to it. But notice that by default, this is a default rule. It's going to deny all traffic. So, which is not bad practice, actually. Okay. Well, so let's do a quick review. So when we structure our infrastructure, we've got a VPC that's got networking information. Here's the networking information. You can see it right here, right? Oop, sorry. Let's take that away. Here's the networking information. Bear with me just one second. I'm having some issues. All right, so here's the networking information. That means that this and this make up the host. This means I have 65,000 available IP addresses. But then what's going to happen is I'm going to slice this up into subnets, right? Now, as we keep going with this, what's going to happen is that traffic's going to come in and hit the route table first. So traffic's coming in from the internet, and the route table says, oh, go here. You're looking for this subnet. And then what happens is that it's got to get past. Oh, you just kind of skipped all that. Hold on. It's got to get past the network ACL here. Then it's got to get past the security group here. And then it gets to the instance. That's what happens. If we're going in reverse, what happens now is that then, this traffic is going through, right? If it's going out, it has to get out the security group, past the subnet, past the network ACL, and then it goes out to the route table, right? So just know that the order of evaluation is first the route table, then the network control list, which by the way is the perimeter boundary for the subnet. Then it hits the security group, which is the firewall for the instance, and it does that whole thing in reverse order when it goes out. So inbound traffic hits the subnet first, and then hits the security group. Outbound traffic hits the security group first, then the network ACL, and then the route table. Questions on any of that? Oop, hold on just one second while I'm talking. me just fix something really quick. Oh yeah, pre-warmed. Good. Just want to make sure. All right. Now, remember that to enable internet access for an instance, you have to have an internet gateway attached to your VPC. You have to have a route table that points to the internet gateway, right? See this here? You have to have either a public IP address or an elastic IP address. Public IP addresses, by the way, are subnet rotating. So they're just rotated public IP addresses that Amazon provides. Elastic IP addresses are static IP addresses that you provision and request. And then you have to make sure that your network access control list and your security groups for the instance are not blocking any traffic. So remember, internet gateway, route table, IP address, public IP address, right? Or elastic IP, and then your security groups have to allow that traffic. Questions? Comments? Okay, let's do a little knowledge check and then we'll roll into our last lab and then we will be done for the day. 1, where are VPCs deployed? Are VPCs deployed in a local zone, an availability zone, a subnet, a CIDR block, or a region? I'll take an answer from anyone.
AZs.
AZs, availability zones? Subnets are deployed into availability zones, but I don't think that VPCs are deployed just into availability zones.
Regions?
Regions. VPCs are region-wide, right? So make sure VPCs are region-wide, subnets are availability zone specific.
Okay.
Good. Security groups allow all traffic in by default. You must set specific rules to specifically block unwanted traffic. Is it true that when you launch an EC2 instance, by default, the internet can always get into the system? Because that's basically what it's saying. Is that true or false?
False.
That's false. By default, Amazon is not going to have a default insecure configuration. So they're, by default, no one can get to your box if you start it up. You have to actually put a hole in the firewall in your security group for someone to get to your box, even if it's able to get to the internet. So that's false. Good. Any questions about the networking or VPCs or subnets, the role of NAT gateways and internet gateways? I know we talked about this at the beginning. I hope you feel like you're learning something, or at least you're getting refreshed on some things that you may not have known. Because this is pretty heady stuff, right? We're deep into the AWS weeds at this point in time. Any questions before we roll forward? Okay. All right, we're on our last lab, creating a virtual private cloud. This is the last lab for the day. All right, so we're going to create a virtual private cloud, and you're answering the question of, or the need, I guess, of I need a private network in the cloud. So we are going to use Amazon VPC. We're going to do some VPC peering, and you will test using EC2 and RDS. So here's what's going to happen. You're going to create an internet gateway, a public subnet, a private subnet, route tables for the associated subnets, and then you're going to test the public subnet by launching an app server, and you're going to connect to it. Here's an optional challenge as well, is that you can create a VPC to VPC peering connection, configure the route table so that the peering connections can work, and you're going to connect by connecting the application up to the application to the database. In Quick Labs, this is going to be lab 3. The instructions, of which there's 6 of them, plus the challenge, are all listed right here, step by step. Make sure that you close out any tabs for any of the previous labs, and even log out, right, to make sure that you're not logged in. Make sure that the challenge here, as far as configuring VPC peering, is here, right? So if you want to do that optional challenge, this is typically a 30-minute lab. So I would say go for it, hit start, get cracking. As soon as you are done, you're done for the day. We're finite at this point. So what will happen is we're going to pick it right back up at 8:30. I'm going to do a quick review, and then we're going to roll right back into the second part of the networking content. And we're going to move out for the rest of our day. So just be prepared, by the way, tomorrow morning. It is a little lecture heavy because it's like 3 hours of lecture. But go ahead and start your lab. Don't let me slow you down. But I was like looking, and I've taught this class many times, and I always forget. It's like 3 hours, 2.5 hours of lecture out in the get-go. So we'll be sure to take a break early in the morning to make sure that I give you space to refresh. But just know that we are totally on target track. And so tomorrow we'll make sure I give you some space to chill just a little bit. Okay, I'm here. Let me know if you need anything. If I happen to step away, if you put it in the chat, it will instantly pop up on my phone. So just let me know if you need anything, okay? Otherwise, go and conquer the lab. If I don't talk to you, have a fabulous day. But I'm going to stay here at least until 4:30, probably beyond. So if you have any problems, just let me know. Let's get it.